An object from another star system is moving through our solar system right now, but it's not behaving like any comet we've ever seen. Its chemistry is wrong, its trajectory is too perfect, and at its closest approach to the sun, it did something that has astronomers questioning everything. What we learn from 3i Atlas could rewrite our understanding of planetary systems across the galaxy, reveal how common or rare technological civilizations might be, and answer whether we've just witnessed our first glimpse of alien engineering. NASA's James Webb Space Telescope detected a carbon dioxide to water ratio of 8:1, among the highest ever recorded. Harvard astrophysicist Avi Loeb has cataloged 9 distinct anomalies, and the object's orbital alignment with our planetary plane, statistically, it shouldn't exist.
But here's what keeps scientists awake at night. Was Thales simply passing through, or was it looking for something? Tonight we'll journey through the complete story of this mysterious visitor, from its discovery on a summer night in Chile to the controversial debates dividing the scientific community, from the chemistry that doesn't add up to the possibility that we may have just missed humanity's first contact with extraterrestrial technology. We'll explore what we know, what we suspect, and what remains hidden in the data still being analyzed by observatories around the world. So settle in, dim the lights, and join me as we follow an ancient traveler on its brief passage through our cosmic neighborhood, a visitor that arrived carrying secrets from another star and perhaps, just perhaps, carrying something more. July 1st, 2025, the Atacama Desert in Chile, 3,000 meters above sea level, where the air is thin and the stars burn with uncommon clarity.
The Atlas Telescope, asteroid, terrestrial impact. Last alert system swept its robotic eye across a predetermined section of sky. It does this every clear night, hunting for asteroids that might threaten Earth, cataloging the small bodies that populate our solar system's darkness. The software algorithms that process Atlas data are designed to notice motion, to detect objects that shift position against the fixed backdrop of distant stars. On this particular night, the system flagged something unusual. The object was faint, barely discernible, against the dense star fields of Sagittarius, the constellation that points toward the heart of our Milky Way galaxy. Initial measurements were crude position and brightness only, but they were enough to trigger the standard protocol. The detection was logged, time-stamped, and automatically transmitted to the Minor Planet Center in Cambridge, Massachusetts, the international clearinghouse for observations of comets, asteroids, and other small solar system bodies. Within hours, other telescopes turned their attention to the same patch of sky. Follow-up observations are critical, because a single detection could be an artifact, a cosmic ray striking the detector, a satellite passing through the field, or simply a flaw in the data processing. But when multiple independent observers confirm the same object in the same location, moving in a consistent direction, you know it's real. The confirmation came quickly, too quickly for comfort. Amateur astronomers and professional observatories alike began reporting positions for the object designated C-2025N1. The C indicated a comet, or at least something that would likely develop a coma, that fuzzy envelope of gas and dust that distinguishes comets from bare rock asteroids. The 2025N1 marked it as the first such object discovered in the first half of July 2025. But as the orbital calculations refined with each new observation, something extraordinary emerged from the numbers. The object was not orbiting the sun. Let me be precise. The object was clearly responding to the sun's gravity, following a trajectory shaped by that immense gravitational well. But the shape of that trajectory was wrong. Not an ellipse, not even a barely bound parabola. The orbit was hyperbolic, open on both ends, meaning the object was moving too fast to be captured. It had come from somewhere else entirely, from the space between stars. And after its brief swing around our sun, it would return to that interstellar void, never to return. The astronomical community has a specific term for such objects: interstellar interlopers. Before 2017, we had never confirmed the existence of one. The physics suggested they should exist debris ejected from other planetary systems during the violent processes of planet formation, wandering the galaxy for millions or billions of years until chance brings them near another star. But detecting them required seeing something extremely small and dark, moving extremely fast through our sky, and doing so before it vanished back into the cosmic ocean. Then came Oumuamua in 2017, the first confirmed interstellar visitor, an elongated object tumbling through space that showed a small, mysterious acceleration inconsistent with gravitational predictions alone. The debate about Oumuamua's nature continues to this day, with some scientists suggesting exotic outgassing from unusual ices, while others, most notably Harvard's Avi Loeb, have argued that we cannot rule out artificial origins. 2 years later, in 2019, we detected 2I Borisov, the second interstellar visitor. This one behaved like a perfectly normal comet, complete with a beautiful tail and spectroscopic signatures matching solar system comets almost exactly. Borisov was comforting in its ordinariness, proof that not every interstellar object needs to be exotic or controversial. Now we had a third. C2025N1 earned the informal designation 3 Atlas, marking it as the third confirmed interstellar object discovered by the Atlas system. But unlike Borisov, 3I Atlas would not be ordinary. Unlike Oumuamua, it wouldn't remain silent and mysterious. This visitor was about to reveal things about the universe beyond our solar system that would challenge our assumptions and divide scientific opinion in ways we hadn't experienced since Galileo turned his telescope toward Jupiter's moons. The discovery was announced formally on July 6, 2025. By then, astronomers had already begun the intensive observation campaign that would continue for months. Every telescope with available time, every space-based observatory with the capability, every amateur astronomer with sufficient equipment, all focused their attention on this tiny dot of light racing through Sagittarius. Because opportunities like this are fleeting. Interstellar visitors don't linger. They arrive from the deep black, make their closest approach to the sun, and then accelerate back toward interstellar space, dimming with distance until even our most powerful telescopes lose them against the background stars. If we wanted to understand 3I Atlas, we had only months, perhaps as it would turn out only weeks, to observe it clearly before its geometry relative to Earth and Sun made detailed study impossible. The race was on. A race against orbital mechanics, against the dimming of distance, against the complications of Earth's rotation and the Sun's glare. A race to gather every possible photon of light, every spectral signature, every clue that might reveal where this object came from, what it was made of, and whether it was simply a frozen relic from another world's creation or something else entirely. Something that would force us to reconsider whether we are truly alone in this galaxy. In astronomy, numbers tell stories. The orbit of 3I Atlas tells a story of speed, of ancient origin, of a journey, measured not in years but in epochs. The orbital eccentricity measured 6.14. To understand what this means, think of eccentricity as a measure of how far an orbit deviates from a perfect circle. Earth's orbit has an eccentricity of 0.007, nearly circular. A comet in a highly elongated elliptical orbit might have an eccentricity of 0.9, stretching from the outer solar system to nearly the Sun's surface. At an eccentricity of exactly 1.0, the orbit becomes a parabola, the mathematical boundary between bound and unbound trajectories. Anything above 1.0 escapes. The object is hyperbolic, meaning it will never return. At 6.14, the orbit of 3I Atlas isn't just barely unbound. It's dramatically hyperbolic, carrying enormous excess velocity relative to objects gravitationally tied to our sun. That excess velocity was calculated at approximately 60 kilometers per second. Imagine moving at 216,000 kilometers per hour, or about 134,000 miles per hour. To put this in perspective, Earth orbits the Sun at 30 kilometers per second. The escape velocity from Earth's surface is about 11 kilometers per second. The fastest human-made object, the Parker Solar Probe, reaches speeds of 192 kilometers per second, but only by diving deep into the Sun's gravity well and using multiple planetary flybys for gravitational assists. 3I Atlas achieved its speed simply by falling through interstellar space for an incomprehensibly long time, carrying the velocity imparted when it was ejected from its birth system, modified by countless subtle gravitational tugs from passing stars over millions of years. Where did it come from? The trajectory, when traced backward through time, pointed toward Sagittarius, the constellation that lies in the direction of our galaxy's central bulge. This doesn't necessarily mean the object originated from the galactic core some 26,000 light-years away. More likely it came from a star system somewhere along that line of sight, perhaps hundreds or a few thousand light-years distant. The motion of stars around the galaxy, the slow cosmic dance called galactic rotation, would have scrambled any clear trail connecting 3I Atlas to its specific parent star. Imagine trying to trace a single leaf back to its tree after it has floated down a river for 100 miles. The current has twisted it, eddies have spun it, other debris has bumped it off course. By the time you find it lodged against a riverbank, its origin is lost to chaos. So it is with objects wandering between stars. The size of 3I Atlas remained frustratingly uncertain. Determining the size of a distant dim object requires knowing two things: how much light it reflects, measured as absolute brightness, and what fraction of incoming sunlight it reflects, called albedo. The absolute brightness could be measured directly. The albedo had to be assumed based on what we know about similar objects, and that assumption carried enormous uncertainty. If 3I Atlas had a dark, carbon-rich surface like some asteroids and comets absorbing most of the sunlight that touched it, then the object would need to be quite large to reflect the amount of light we observed. Early estimates suggested a nucleus diameter of up to 5.6 kilometers, or about 3.5 miles across. That would make it larger than most comets that pass through the inner solar system, a substantial mountain of ice and rock tumbling through the void. If instead, the surface was bright and reflective, covered in fresh ice or perhaps something more exotic, the object could be much smaller. The lower bound of estimates dropped to just 440 meters, less than half a kilometer. That's small, roughly the size of 5 city blocks on a side. This factor of 10 uncertainty in size translated to a factor of 1,000 in estimated mass. Mass matters critically for understanding the object's behavior. A small, low-mass object experiences greater accelerations from subtle forces like solar radiation pressure, the gentle push of sunlight on any surface. A large, massive object shrugs off these effects, responding only to gravity and any active forces like outgassing jets. The uncertainty would plague interpretation of every observation that followed. Hubble Space Telescope observations in late July attempted to constrain the size more tightly. Hubble's exquisite resolution revealed the object's coma, that teardrop-shaped cocoon of dust and gas surrounding the nucleus. The images showed the coma clearly, but the nucleus itself remained unresolved, too small and too embedded in the surrounding haze to measure directly. The astronomers could only say that the solid nucleus was smaller than Hubble's resolution limit at that distance, which didn't narrow the range significantly. The trajectory carried 3I Atlas on a path that would bring it relatively close to the Sun by interstellar visitor standards, perihelion. The point of closest approach was calculated to occur on October 29-30, 2025 at a distance of 1.35 to 1.44 astronomical units from the Sun's center. One astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers or 93 million miles. So, 3i Atlas would pass the Sun at a distance slightly greater than Earth's orbit, roughly equivalent to passing between Earth and Mars. For comparison, Oumuamua passed within 0.25 AU of the Sun, experiencing far more intense heating and solar radiation. 2i Borisov stayed farther out around 2 AU at perihelion. The trajectory of 3i Atlas fell comfortably in the middle range, close enough for significant solar heating to sublimate ices and produce observable activity, but not so close that the object would experience extreme thermal stress or risk fragmentation. The inclination of the orbit measured approximately 175 degrees. Orbital inclination tells you how tilted an object's orbit is relative to the ecliptic plane, the flat disk defined by Earth's orbit. An inclination of 0 degrees means the object orbits in the same plane as Earth. An inclination of 90 degrees means the orbit is perpendicular, diving up or down through the solar system.
An inclination above 90 degrees indicates retrograde motion moving opposite to the direction planet's orbit. At 175 degrees, Atlas was moving retrograde, but with its orbital plane tilted only about 5 degrees from the ecliptic. This alignment was unexpected, statistically surprising. Why? Because interstellar objects should arrive from random directions in space. The galaxy has no preferred orientation relative to our solar system's ecliptic plane. Objects ejected from other planetary systems billions of years ago and traveling through the galaxy's chaotic gravitational environment should arrive with orbital inclinations distributed uniformly across all possible angles. Finding an interstellar visitor aligned so closely with our planetary plane is like throwing a dart at a globe from across a room and hitting within a few degrees of the equator. Possible, certainly, but improbable enough to raise questions.
Is it coincidence? A fluke of chance that will seem less surprising once we've detected hundreds of interstellar visitors and can assess the full statistical distribution, or is there a selection effect? We don't understand some physical process that makes objects arriving in the ecliptic plane easier to detect or more likely to pass close to the Sun, or as some would argue, does the alignment suggest something about the object's origin or purpose? These questions would gain urgency in the months ahead as more data revealed more anomalies. But in those early July days, the numbers painted a clear initial picture. 3i Atlas was a genuine interstellar visitor carrying tremendous speed, approaching perihelion on a moderately close trajectory and exhibiting at least one statistically unusual property in its orbital alignment. The stage was set. The visitor was identified. Now the true investigation would begin as astronomers worldwide turned their most powerful instruments toward this ancient traveler, seeking to decode the secrets frozen into its icy nucleus billions of years ago in a planetary system orbiting a star we will likely never identify. In the cold darkness between stars, chemistry proceeds according to well-understood rules. Temperature hovers just a few degrees above absolute zero. Radiation from distant stars provides energy for occasional reactions, but mostly atoms and molecules simply drift frozen into solid grains or clinging to the surfaces of ice particles in vast molecular clouds. When planetary systems form, they inherit this chemistry. The protoplanetary disk surrounding a young star contains whatever mix of elements and compounds existed in the molecular cloud that collapsed to birth the star. Over millions of years, these materials condense, collide, and accrete into planets, asteroids, and comets. The chemistry of those bodies tells us about the conditions in which they formed. This is how we read cosmic history. By analyzing the light reflected or emitted by distant objects, measuring which wavelengths are absorbed or enhanced, we can identify specific molecules and deduce compositions. It's forensic astronomy detective work conducted across hundreds of millions of kilometers of empty space. When spectroscopic observations of 3I Atlas began arriving in August 2025, they revealed something strange. The James Webb Space Telescope, humanity's most powerful infrared observatory, turned its near-infrared spectrograph toward 3I Atlas on August 6th. JWST's sensitivity and spectral resolution are unmatched, capable of detecting faint signals from molecules that would be invisible to lesser instruments. The data would take weeks to fully analyze, but preliminary results were shared within days. The object was extraordinarily rich in carbon dioxide, not just rich, dominated by it.
The carbon dioxide to water ice ratio measured approximately H1, meaning for every molecule of water ice in the coma, there were 8 molecules of carbon dioxide ice sublimating from the nucleus. This ratio is among the highest ever recorded for any comet, solar system, or interstellar. Normal solar system comets show the opposite pattern. Water ice dominates, typically comprising 70 to 90% of volatile materials. Carbon dioxide exists certainly often at levels of 10 to 30% relative to water, but an 8:1 ratio inverts the expected composition entirely. Why does this matter? Because water and carbon dioxide form under different conditions and tell us about different environments. Water requires hydrogen and oxygen, the most abundant reactive elements after helium. It freezes at relatively high temperatures compared to other volatiles, around 273 Kelvin, at 1 atmosphere of pressure, though in the near vacuum of space, and extremely low temperatures, water ice exists far colder. Carbon dioxide forms from carbon and oxygen. It's more volatile than water, sublimating at lower temperatures, which is why dry ice on Earth sublimates directly from solid to gas at room temperature and pressure. In the cold outer regions of a protoplanetary disk, both water and carbon dioxide freeze out, but their relative abundances depend on the disk's temperature profile, the availability of carbon versus oxygen, and the specific location where the comet formed. An 8:1 CO2 to water ratio suggests formation in an extremely cold environment, perhaps in the outer reaches of a planetary system where carbon dioxide ice could accumulate preferentially.
Or it might indicate a parent star system with unusual elemental abundances richer in carbon relative to oxygen than our Sun. The JWST data revealed other molecular species as well. Carbon monoxide, even more volatile than carbon dioxide, appeared at moderate levels. Carbonyl sulfide, an unusual molecule containing carbon, oxygen, and sulfur, showed up in trace amounts, and water, though present, remained a minority component. The SphereX Space Observatory, NASA's spectrophotometer for the history of the universe, confirmed the JWST findings independently. SphereX observed 3I Atlas from August 7-15, gathering spectral data across a broader wavelength range with lower resolution than JWST, but providing valuable confirmation that the carbon dioxide detection was real and not an artifact of JWST's instruments. But chemistry wasn't the only anomaly. Polarization studies added another layer of mystery. Polarization measurements examine how light waves oscillate.
Sunlight is unpolarized, meaning its electromagnetic waves vibrate in all directions, perpendicular to the direction of travel. When that light reflects off dust particles in a comet's coma, it becomes partially polarized, with the degree and direction of polarization depending on the particle's size, shape, composition, and the angle between the sun, comet, and observer. Most comets show a characteristic polarization curve. At very small phase angles, when Earth views the comet nearly head-on with the sun behind us, the polarization is slightly negative. As the phase angle increases, polarization crosses through zero and becomes positive, reaching a maximum around 90 to 100 degrees phase angle before declining again.
This pattern results from how light scatters off irregular dust grains. Negative polarization at small angles arises from coherent backscattering, a quantum interference effect, where light waves scattered from different parts of a grain constructively interfere when viewed exactly opposite the light source. 3i Atlas showed negative polarization all right. Extreme negative polarization. Observations from the Very Large Telescope. Nordic Optical Telescope and Rosen Observatory in July and August 2025 measured polarization values significantly more negative than any solar system comet at comparable phase angles. What does this mean? It suggests the dust grains in the coma have unusual properties. Perhaps they're unusually large or small compared to typical comet dust. Perhaps they have different shapes, maybe more spherical or more elongated. Perhaps their composition differs with higher metal content or different mineral phases than the silicate and carbonaceous dust we see from solar system comets.
A paper published on the Arxiv preprint server in August 2025 by polarimetry experts noted the anomaly, but declined to speculate beyond natural explanations. The authors suggested that dust from a metal-rich protoplanetary disk, or grains, coated with organic materials not common in our solar system might produce such signatures. Other researchers pointed to the possibility of cryovolcanism, where pressurized volatiles beneath an insulating crust occasionally burst through ejecting particles with different properties than dust slowly eroded by steady sublimation. Or perhaps the dust had been processed by interstellar cosmic rays during the object's millions of years in the galactic wilderness, altering grain properties in ways we haven't characterized. Then came the claims about metallic emissions.
In September 2025, some reports began circulating online suggesting that spectroscopic observations had detected nickel without corresponding iron, a chemically unusual signature that some interpreted as potentially artificial. The claim centered on the detection of specific spectral lines consistent with nickel emissions, possibly from nickel carbonyl compounds, without the iron lines that should accompany nickel in natural astrophysical environments. Why would this be significant? Nickel and iron are cosmochemical twins formed together in stellar nucleosynthesis and typically found together in meteorites, asteroids, and comets in roughly solar proportions. Separating nickel from iron requires industrial processes or extremely specific geochemical conditions that are rare in natural settings. Nickel carbonyl or nickel tetracarbonyl is particularly suspicious because it's used in terrestrial industrial processes for refining nickel. It forms when carbon monoxide gas reacts with metallic nickel at moderate temperatures and pressures. Finding it in space would be extraordinary. However, and this is critical, no peer-reviewed papers confirmed the detection of nickel carbonyl or unusual nickel-to-iron ratios in 3i Atlas as of late 2025. The claims remained in the realm of preliminary reports, informal communications, and public statements by researchers advocating for more exotic interpretations. Mainstream astronomers responded cautiously. Metallic emissions can arise from dust grains containing iron-nickel alloys common in meteoritic material. Sublimating ices can release metal atoms trapped in the ice matrix. Interpreting spectral lines requires careful analysis to avoid confusing one element's signature for another's or mistaking instrumental artifacts for real signals. Without confirmation from multiple independent groups using different instruments and methods, the nickel anomaly remained unverified. Interesting, if true, but requiring much stronger evidence before acceptance. So what picture emerges from this chemical puzzle? We have an object dominated by carbon dioxide ice to an unprecedented degree. We have dust with unusual polarization properties suggesting atypical grain characteristics. We have preliminary unconfirmed claims of unusual metallic signatures. And we have all of this wrapped in a visitor from another star system carrying the chemical fingerprint of an environment we've never sampled. Three interpretations compete. First, The conservative view. 3i Atlas formed in a planetary system with compositions or conditions significantly different from our own. Perhaps it's a fragment from a carbon-rich planet, a world where carbon compounds dominate over water. Perhaps it formed in the extreme outer reaches of its system where carbon dioxide ice accumulated preferentially over billions of years. The unusual polarization reflects dust from an exotic mineralogy we haven't encountered in solar system samples. Unusual, yes. Unprecedented in our limited experience, certainly, but still natural, still explicable through known chemistry and physics, just applied in unfamiliar combinations. Second, the exotic natural view. What if 3i Atlas is even stranger than a typical interstellar comet? Some astrophysicists speculate it could be a fragment of a disrupted exoplanet, a piece of a world torn apart by tidal forces from a too close stellar encounter, or ejected in a violent planetary collision. Planetary materials undergo different chemical processing than comets, experiencing higher pressures and temperatures that create different mineral assemblages. If this interpretation is correct, 3i Atlas becomes a sample of an actual alien world, not just the icy debris from planetary formation, but the planet itself. The scientific value would be immense, but the object remains entirely natural. Third, the controversial artificial hypothesis. This is speculation and must be labeled as such, but given the unusual chemistry and the trajectory anomalies we'll discuss later, some researchers have suggested we cannot completely rule out the possibility that some of what we're observing reflects manufacturing processes rather than natural astrophysical chemistry. Industrial refinement of materials, protective coatings designed to survive interstellar travel, or even propellants and engineering materials could potentially produce signatures that differ from natural cometary chemistry. However, no definitive evidence supports this interpretation, and the burden of proof for such an extraordinary claim remains astronomically high. The chemistry of 3i Atlas doesn't prove anything extraordinary on its own, but it establishes that this visitor is unusual enough to warrant careful attention as we examine every other aspect of its behavior, especially what happened during those crucial hours when it passed closest to the sun and vanished temporarily behind solar glare. Close your eyes and imagine our solar system from above, looking down on the sun and planets from a vantage point far out in space. You would see a remarkably flat structure. The 8 planets all orbit in nearly the same plane, the ecliptic defined by Earth's orbital path. This flatness isn't coincidence. It's a fossil record of the solar system's birth. 4.5 billion years ago, a cloud of gas and dust collapsed under its own gravity. Conservation of angular momentum, the tendency of rotating systems to maintain their spin, caused the collapsing cloud to flatten into a disk. The sun formed at the center. The planets coalesced from material in that disk. Everything inherited the disk's orientation, which is why, looking at the solar system edge-on, you would see an almost 2-dimensional structure, despite the 3-dimensional vastness of space. Now imagine objects arriving from interstellar space. The galaxy has no preferred orientation relative to our ecliptic. Stars orbit the galactic center in complex 3-dimensional paths. Objects ejected from those stars' planetary systems inherit random velocities in random directions. When one of those objects happens to wander close enough to our sun for us to detect it, the direction from which it arrives should be essentially random. Statistically, if we detected many interstellar visitors, we would expect their orbital inclinations to be distributed uniformly. Some would arrive moving in the same direction as our planets. Some opposite. Many would dive up or down through the plane of the solar system at steep angles. There should be no preference, no pattern. 3i Atlas arrived, moving retrograde opposite to the planet's motion, which is fine. About half of random arrivals should be retrograde simply by chance. But its orbital plane was inclined only about 5 degrees from the ecliptic. It was moving almost exactly in the plane of our planetary system, just traveling the opposite direction. How unlikely is this? The mathematics are straightforward. If inclinations are distributed uniformly across all possible angles from 0 to 180 degrees, the probability of any given object arriving within 5 degrees of the ecliptic is quite small, roughly 5.5%. Not impossible. Not remotely impossible. But surprising enough that when it happens, astronomers take notice. With a sample size of 3 confirmed interstellar visitors, we can't draw statistical conclusions. Oumuamua had an inclination of about 122 degrees, which put its orbital plane at about 58 degrees from the ecliptic. Borisov came in at 44 degrees. Neither of those was particularly aligned with our planetary system. Then 3I Atlas arrives almost perfectly in the plane. Is it coincidence? Almost certainly yes. When you observe rare events with small sample sizes, sometimes you see improbable things simply because individual outcomes, while unlikely, must be something. But there's a second possibility: selection bias. Perhaps objects arriving close to the ecliptic plane are easier for us to detect because their trajectories carry them closer to the sun and planets. Passing through regions of sky we monitor more intensively with our asteroid detection surveys. Objects diving through the solar system at steep angles might pass through less surveyed regions and evade detection. If this selection effect is strong, we might preferentially discover the aligned objects while missing the randomly oriented ones. Testing this hypothesis requires more data. We need to detect dozens of interstellar visitors and carefully account for our observational biases. Only then can we determine whether 5-degree alignments occur more often in our detected sample than we would expect from random chance. Until we have that data, the alignment remains an intriguing curiosity, worth noting, worth studying, but not on its own evidence of anything beyond natural variation. However, some researchers have suggested a third possibility, one that ventures into speculative territory. What if the alignment is intentional? This is speculation. I want to be absolutely clear about that, but let's follow the logic. If an advanced civilization wanted to send a probe to explore other planetary systems, how would they choose trajectories? Random directions would work if the goal is simply to explore as much of the galaxy as possible. But if the goal is to observe planetary systems specifically to study worlds where life might exist, then aligning the probe's trajectory with target system's ecliptic planes might make sense. Why? Because staying near the ecliptic allows the probe to potentially encounter multiple planets in sequence. A trajectory diving perpendicular to the ecliptic might pass near one planet but miss all the others, separated by hundreds of millions of kilometers in the orbital plane. A trajectory aligned with the ecliptic could potentially pass within observation distance of several worlds in one visit. This argument assumes that alien civilizations would think like human mission planners, optimizing trajectories for scientific return. It assumes they would target planetary systems for study rather than simply wandering the galaxy indiscriminately. It assumes a level of intentionality and purpose that may not apply to objects that could have been traveling for millions of years, far longer than any civilization might persist. These assumptions are enormous, unverifiable, deeply anthropocentric, which is why mainstream astronomers dismiss the intentional alignment hypothesis as baseless speculation unsupported by evidence. But the question lingers in the minds of those who study interstellar visitors. Why this plane? Why nearly perfect retrograde ecliptic alignment for an object arriving from random interstellar space? Is it truly just chance? Or are we missing something about the physics of ejection and galactic travel that makes such alignments more common than random probability suggests? The trajectory of 3I Atlas carried it inbound from the direction of Sagittarius, sweeping through the inner solar system on a path that would bring it relatively close to several planets. On October 3, 2025, it would pass within approximately 29 million kilometers of Mars. Not close by planetary standards, but close enough that spacecraft orbiting Mars, particularly the Mars Reconnaissance Orbiter with its powerful high-rise camera, might acquire images if mission controllers chose to target the visitor. On November 3, 2025, the trajectory would carry 3I Atlas within about 97 million kilometers of Venus. Again, not a particularly close approach, but within the realm where Venus orbiters might observe it if the geometry and spacecraft capabilities aligned. On December 19, 2025, Earth would experience its closest approach to 3I Atlas at approximately 1.8 astronomical units, about 270 million kilometers. Far beyond the orbit of the Moon, no threat whatsoever, but close enough for ground-based telescopes to acquire excellent data. And finally, on March 16, 2026, the object would pass within about 54 million kilometers of Jupiter, potentially visible to NASA's Juno mission orbiting the gas giant. This sequence of planetary encounters all possible because the object's trajectory lay in the ecliptic plane, provided multiple opportunities for spacecraft observations from different vantage points. Each encounter would refine our understanding of the object's orbit and potentially reveal details about its surface rotation and activity that Earth-based observations might miss. From an observational standpoint, the ecliptic alignment was fortuitous. It maximized our chances to study this rare visitor using all available assets across the solar system. From a theoretical standpoint, the alignment remained a puzzle piece that fit awkwardly into the natural explanation framework. Not impossible, not proof of anything, but unusual enough to keep researchers asking questions and to fuel speculation among those inclined toward more exotic interpretations. The numbers don't lie, but they also don't tell the whole story. Trajectory is just one piece of the puzzle. To understand 3I Atlas fully, we needed to watch what it did when the sun's heat reached maximum intensity during perihelion passage. We needed to see whether the object behaved exactly as physics and chemistry predict for a natural comet, or whether something unexpected would occur during those crucial hours when the visitor swung past our star and vanished temporarily from our view. October 29, 2025. The moment astronomers had been anticipating for months finally arrived. 3I Atlas reached perihelion, its closest approach to the Sun, passing approximately 1.35 to 1.44 astronomical units from our star's blazing surface. For a comet, perihelion is the ultimate test. This is when solar radiation reaches maximum intensity, when temperatures on the sunlit side soar, when volatile ices buried beneath protective layers of dust finally sublimate in earnest, releasing gas that expands rapidly into the vacuum of space and drags dust particles along in powerful jets. Perihelion reveals what a comet is made of. It's when hidden ices vaporize, when weak structures fracture and collapse, when objects sometimes fragment entirely under the thermal stress and tidal forces. It's the moment of truth, but there was a problem, a frustrating, unavoidable problem of geometry and solar glare. From Earth's perspective, on October 29, 3I Atlas lay almost directly behind the Sun. The configuration is called solar conjunction, when an object's position in the sky places it too close to the Sun's overwhelming brightness for direct observation. Telescopes cannot safely point near the Sun. The flood of photons would saturate detectors, ruin instruments, and prevent any meaningful data collection. For approximately 2 weeks, around perihelion, 3I Atlas became essentially unobservable from Earth. We could track it until mid-October as it approached. We could reacquire it in mid-November as it emerged from behind the Sun and its angular separation increased. But during the critical hours when the object swung through perihelion, when any unusual activity would be most apparent, we were blind. This timing raised questions, uncomfortable questions for those inclined towards suspicious thinking. Was it coincidence that the visitor's closest approach occurred precisely when Earth-based observations became impossible, or was there something about the trajectory, some intentional element that exploited this blind spot? The answer almost certainly is coincidence. Perihelion timing depends on the object's orbital parameters, which in turn reflect whatever gravitational slingshots and perturbations shaped its journey through interstellar space over millions of years. There's no reason to invoke intentionality when orbital mechanics provides a complete explanation. But the timing meant that detecting any anomaly during perihelion would be extraordinarily difficult. If the object performed a maneuver, fired engines, released secondary objects, or showed any behavior inconsistent with natural comet activity, we wouldn't see it happen in real time. We could only infer it afterward by carefully comparing the pre-perihelion trajectory with post-perihelion observations and checking whether the object's position and velocity matched predictions or showed unexplained deviations. This is where the Oberth effect enters the discussion. In orbital mechanics, the Oberth effect describes how the efficiency of a propulsive maneuver depends on velocity.
When you fire an engine to accelerate, the kinetic energy you gain depends on both the thrust and your velocity at the moment of the burn. Specifically, the energy gain is proportional to velocity times thrust. This means the same thrust applied when you're moving faster produces a larger total energy change than the same thrust applied when moving slower. Perihelion is when any object orbiting the Sun moves at maximum velocity, accelerated by the Sun's gravity to its fastest speed along the orbital path. For 3I Atlas, perihelion velocity would peak at approximately 60 kilometers per second relative to the Sun, even faster than its excess hyperbolic velocity because of the gravitational acceleration during infall. If you wanted to change an object's trajectory using a thruster or rocket engine, perihelion is the optimal time to do it.
A small thrust applied at perihelion produces a much larger change in total orbital energy than the same thrust applied when farther from the Sun and moving slower. This is not speculation, it's orbital mechanics. 101 used routinely by spacecraft mission planners to design fuel-efficient trajectories. The Oberth effect is why spacecraft often dive close to planets to perform maneuvers exploiting the high velocity at closest approach to maximize the bang for their propellant buck. So if 3I Atlas were not a passive comet but rather a probe with propulsion capabilities, and if that probe wanted to alter its trajectory, perihelion would be the logical moment to act. The timing would accomplish two things: maximum efficiency from the Oberth effect and maximum concealment from Earth-based observers due to solar conjunction. This reasoning led some researchers, most prominently Avi Loeb, to describe perihelion as the acid test for 3I Atlas. If the object performed an unexpected maneuver, if post-perihelion observations showed trajectory deviations inconsistent with natural outgassing, then we would have evidence demanding serious consideration of artificial origins. But what would such evidence look like? How would we distinguish an engineered trajectory change from natural comet behavior? The key is precision. Astrometry, measuring the object's position with extreme accuracy over many nights and comparing those measurements to predictions based on gravitational models. Natural comets show small, non-gravitational accelerations caused by asymmetric outgassing. When gas jets from the nucleus, they act like tiny rockets pushing the comet slightly. These accelerations are small, typically measured in millimeters per second, and their direction usually correlates with the Sun's position because solar heating drives the outgassing. An engineered thrust would potentially show a different signature.
The direction might not correlate with solar heating. The magnitude might be larger than outgassing models predict. The timing might show sudden onset and cutoff rather than the gradual ramp-up and decline expected from ice sublimation as solar distance changes. The challenge is that natural comet behavior is complex and not fully predictable. Outgassing patterns depend on the nucleus's shape-rotation surface composition and the distribution of active regions. Some comets fragment, creating confusing acceleration signatures as pieces separate. Some show outbursts, sudden increases in activity that can produce short-duration jets with unpredictable directions. Distinguishing artificial from natural requires not just detecting an anomaly, but ruling out all plausible natural explanations. That's a high bar. As October 29th passed, astronomers could do nothing but wait.
Solar observatories monitored the sun's corona using instruments designed to block the solar disk and reveal the faint outer atmosphere. These instruments can sometimes detect very bright comets passing close to the sun, though 3i Atlas was too far out and too faint to appear in coronagraph images. Some spacecraft, particularly those far from Earth with different viewing angles, might have been able to observe the object during perihelion if their mission teams chose to target it. The stereo spacecraft which orbit the Sun ahead of and behind Earth had viewing geometry that potentially kept 3i Atlas visible even when Earth-based observers lost it. Whether stereo actually observed it and whether any useful data resulted would depend on targeting decisions made by mission operations teams balancing many competing priorities. By early November 3rd, Atlas began emerging from solar conjunction. The angular separation between object and sun as viewed from Earth increased enough that observations could resume. Telescopes turned once again toward the visitor, acquiring positions, measuring brightness, recording spectra. And then came the waiting for analysis. The astrometric data had to be reduced, calibrated, compared against pre-perihelion observations. Orbital models had to be fitted to the combined dataset. Residuals. The differences between observed and predicted positions had to be examined for systematic trends that might indicate real acceleration. This process takes time, days at minimum, often weeks for preliminary results, sometimes months for high-confidence conclusions, as more observations accumulate and uncertainties narrow. What did the data show? As of early November 2025, preliminary analyses suggested that 3i Atlas remained on its predicted trajectory within the uncertainties of the measurements. No large obvious deviation appeared. The object was where gravity said it should be, moving as expected for a passive body responding only to the sun's pull and perhaps small outgassing forces. But uncertainties remained. The measurements were good, but not perfect. The pre-perihelion orbital determination, while well constrained, still carried error bars. A small deviation, something in the range of millimeters per second, sustained over weeks, might exist within the noise and not become apparent until more data accumulated. Some reports circulating online claimed that brightness changes occurred during or shortly after perihelion, showing unusual color shifts from red to blue that could indicate temperature changes inconsistent with passive solar heating. These claims, primarily propagated through social media and blog posts rather than peer-reviewed publications, suggested the object might have increased its temperature substantially, possibly through active energy release. Mainstream astronomers responded with caution. Brightness and color can change for many natural reasons. Outgassing rates vary as different ices sublimate at different temperatures. Dust production creates hazes that redden reflected light when dense and clear when sparse. Rotation brings different surface regions into view, each with potentially different reflectivity and composition. Without detailed photometric analysis from multiple independent observers, brightness claims remained anecdotal. By late November 2025, as this script is being written, the scientific verdict on perihelion passage remained open. No definitive evidence of anomalous behavior had been published in peer-reviewed literature. No confirmed detection of trajectory deviation exceeding natural explanations had been announced by major observatories or space agencies. The acid test, if it was truly a test, appeared to show nothing conclusive. Either Three-Eye Atlas behaved naturally during perihelion, or any unusual behavior was subtle enough to hide within observational uncertainties and the complexities of comet physics. The story, however, was far from over. Observations would continue for months as the object receded from the sun, allowing more time for subtle trajectory deviations to accumulate and become detectable. The December Earth flyby and March 2026 Jupiter encounter would provide additional opportunities to refine the orbit and search for anomalies. And in the background, a debate was intensifying among astronomers and in public discourse about how to interpret what we were seeing or not seeing in the data. That debate would illuminate not just the nature of one mysterious visitor, but the nature of science itself, the process by which we distinguish genuine discovery from wishful thinking, and the challenges of preparing humanity for the possibility, however remote, that we might someday encounter something truly extraordinary among the stars. Science is not a monolith. It's a messy, contentious human endeavor where brilliant minds often reach contradictory conclusions from the same data. Disagreement drives progress, forcing researchers to refine arguments, gather better evidence, and occasionally overturn established theories. The story of Three-Eye Atlas became a stage for one such disagreement, featuring Harvard astronomer Abraham Avi Loeb in the starring role. Loeb is no fringe figure. His credentials are impeccable: professor of astrophysics at Harvard, former chair of the astronomy department, prolific publisher with hundreds of peer-reviewed papers on topics ranging from black holes to the early universe. He's advised PhD students, served on prestigious panels, and contributed significantly to mainstream astrophysics. He's also become one of the most controversial voices in the search for extraterrestrial intelligence, willing to publicly advocate for hypotheses that most astronomers consider extremely unlikely, if not outright implausible. The controversy began with Oumuamua in 2017, when that first interstellar visitor showed a small, unexplained acceleration as it departed the solar system. Most astronomers suggested outgassing from volatiles like nitrogen ice or hydrogen ice, which wouldn't produce visible cometary activity, but could still generate thrust. Loeb, along with postdoctoral fellow Shmuel Bialy, published a paper suggesting that Oumuamua's acceleration could be explained if the object were a light sail, a thin reflective sheet pushed by solar radiation pressure. The paper was technically sound, demonstrating that a light sail geometry could reproduce the observed acceleration. But the implications were explosive. Light sails are artificial objects, engineering artifacts designed to exploit radiation pressure for propulsion. Suggesting Oumuamua might be a light sail implied potential alien technology. The astronomical community's response was swift and mostly critical. Light sails require extreme thinness to achieve sufficient area-to-mass ratios, making them fragile and unlikely to survive interstellar travel. Natural explanations, while requiring some unusual assumptions, remained more parsimonious than invoking alien artifacts.
Extraordinary claims require extraordinary evidence, and the evidence for Oumuamua's artificial origins remained circumstantial at best. Loeb, however, doubled down. He wrote a popular book, Extraterrestrial, arguing that scientists too readily dismiss the possibility of alien technology and should remain open to evidence-based speculation. He founded the Galileo Project, a research initiative dedicated to searching for signs of extraterrestrial technological artifacts, both in space and in Earth's atmosphere. Critics accused Loeb of attention-seeking, of lowering scientific standards, of providing ammunition for conspiracy theorists, and undermining public trust in science. Supporters praised his willingness to challenge orthodoxy, to ask uncomfortable questions, and to take the search for extraterrestrial intelligence seriously. When Three-Eye Atlas appeared in July 2025, Loeb was primed and ready. Starting in September 2025, Loeb published a series of essays on Medium, a popular blogging platform, outlining what he called 9 anomalies associated with 3I Atlas. These anomalies in Loeb's telling suggested that we should not prematurely conclude the object is natural, but should seriously consider alternative hypotheses, including artificial origins. The 9 anomalies, as Loeb cataloged them, were: 1. The trajectory alignment with the ecliptic plane, which we've already discussed, statistically unusual, though not impossible. 2. A sunward jet, or anti-tail, observed in Hubble images that appeared to point toward the sun rather than away from it, as normal comet tails do, possibly indicating thrust rather than passive pressure from solar radiation and wind. 3. The object's estimated mass potentially 1,000,000 times greater than Oumuamua and 1,000 times greater than 2I Borisov, while moving faster than both, suggesting unusual dynamics or composition.
4. The timing of perihelion during solar conjunction, allowing the object to pass unobserved from Earth at its closest approach, which some interpret as suspicious, though orbital mechanics provides natural explanations. 5. Photometric behavior, showing unusual brightness variations that don't match typical comet models, possibly indicating active thermal management or exotic surface properties. 6. The extreme carbon dioxide to water ratio and potential nickel emissions without iron, suggesting chemistry difficult to explain through natural astrophysical processes. 7. High-resolution imaging, showing morphology, that some interpret as non-random or structured, though mainstream astronomers see only typical comet coma features. 8. The object's passage timing, allowing close approaches to multiple planets, maximizing observational opportunities in a way that some find coincidentally convenient.
9. Brightness increases and color shifts during perihelion that Loeb interprets as potential evidence of active energy release from sources hotter than the sun. Loeb developed what he calls the Loeb scale, a metric for assessing how unusual an interstellar object appears, on a scale from 0, clearly natural, to 10, unquestionably artificial. He rated 3I Atlas at 4 out of 10, indicating significant anomalies that warrant serious investigation without claiming definitive evidence of artificial origins. The mainstream astronomical community's response was less measured than Loeb's own framing. Tom Statler, NASA's lead scientist for solar system small bodies, told journalists, "It looks like a comet. It does comet things. It very, very strongly resembles in just about every way the comets that we know." Other astronomers pointed out that each of Loeb's anomalies, while interesting, has potential natural explanations.
The anti-tail could be a geometric projection effect, a trick of viewing angle that makes outflowing material appear to point sunward when it's actually flowing in a different direction in 3-dimensional space. The unusual mass estimates reflect uncertainties in albedo and nucleus size, not necessarily real mass anomalies. The photometric behavior, while atypical, falls within the range of variability seen in unusual solar system comets. The chemistry, yes, that's genuinely unusual, but unusual doesn't mean artificial. It means we're seeing a sample from a different planetary system with different formation conditions, which is exactly what we should expect from interstellar visitors. What frustrated mainstream astronomers most was the framing. By prominently discussing the possibility of alien technology, even while acknowledging it remains speculative and unproven, Loeb generated media coverage that often simplified the nuances into sensational headlines. Harvard astronomer, interstellar object may be alien probe, or has humanity detected its first alien artifact? These headlines obscure the actual scientific content and inflate public expectations. When the final analysis inevitably concludes that 3I Atlas is a natural comet with some unusual properties, the public feels disappointed, deceived, even as if scientists dangled the possibility of aliens only to snatch it away. This dynamic damages public understanding of science and erodes trust in scientific institutions.
Loeb counters that scientists have a responsibility to discuss all possibilities supported by evidence, not just the comfortable mainstream explanations.
If data suggests something anomalous, we should say so openly rather than downplaying or dismissing it to avoid controversy. Science progresses through challenges to orthodoxy. Galileo was ridiculed for suggesting Earth orbits the Sun. Continental drift was dismissed for decades before plate tectonics became accepted. The invocation of Galileo is both powerful and problematic. Yes, revolutionary ideas often face resistance. But for every Galileo who was right against consensus, there are thousands of contrarians who were simply wrong. Being a maverick doesn't make you correct. Evidence does. And this is where the disagreement becomes most pointed. What counts as sufficient evidence? Loeb argues that the accumulation of anomalies, even if each individual anomaly has possible natural explanations, collectively raises the probability of artificial origins enough to warrant serious investigation. Bayesian reasoning says we should update our priors based on evidence, and enough unusual observations should shift our probability assessment from essentially zero for alien technology to small but non-negligible. Mainstream astronomers counter that each anomaly, when examined carefully, has perfectly adequate natural explanations. Unusual chemistry from an exotic protoplanetary disk. Trajectory alignment from chance or selection bias, photometric variability from complex comet physics. When natural explanations exist, invoking artificial origins violates Occam's razor, the principle that simpler explanations should be preferred absent compelling reasons to complicate things. The burden of proof matters enormously here. Our prior probability for any given object being alien technology should be extremely low, not because we know aliens don't exist, but because we know the vast majority of objects in space are natural. To overcome that low prior requires overwhelming evidence, not just a collection of things we find puzzling. As of late 2025, that overwhelming evidence has not materialized. No peer-reviewed papers have claimed definitive detection of artificial origins. No confirmed trajectory maneuvers beyond natural comet activity. No verified detections of industrial chemicals or technological artifacts. Loeb himself acknowledged in a blog post that the simplest hypothesis is that 3I Atlas is a comet. His goal, he emphasized, was to ensure scientists don't prematurely close the door on alternative explanations, to encourage rigorous investigation rather than quick dismissal. Whether his approach helps or hinders that goal remains hotly debated. What's undeniable is that the Loeb hypothesis and the media attention it generated thrust 3I Atlas into public consciousness in a way that might not have happened otherwise. Millions of people who would never have heard about an interstellar comet became fascinated by the possibility of alien visitors. That fascination comes with risks. It encourages magical thinking, the belief that every anomaly must have an exotic explanation. It feeds conspiracy theories about cover-ups and suppressed evidence. It creates disappointment when reality proves mundane. But it also sparks curiosity. It gets people thinking about the possibility of other intelligences in the universe. It highlights the importance of astronomical research and the need for better instruments to study these rare visitors. The Loeb hypothesis, right or wrong, beneficial or harmful, became part of the 3I Atlas story. And as the data continued accumulating through late 2025 and into 2026, astronomers on all sides of the debate kept watching, kept analyzing, kept arguing about how to interpret what we were seeing, because ultimately, that's how science works.
Not through consensus and comfort, but through tension and challenge, through the friction of competing ideas grinding against each other until truth, or at least the best approximation we can manage, emerges from the process. Let's step back from speculation and ground ourselves in what we know about comets, about how planetary systems form, and about the vast diversity of environments that exist throughout our galaxy. The Milky Way contains somewhere between 100 and 400 billion stars. Most of those stars, perhaps 70% or more, are red dwarfs. Small, cool stars that burn hydrogen slowly enough to shine for trillions of years. Another 20% are stars like our Sun yellow-white main sequence stars with moderate masses and lifetimes measured in billions of years. The remaining 10% includes everything from massive blue giants that live fast and die young to white dwarfs, the dense, cooling remnants of dead stars. Around these stars, planets form. We now know from exoplanet surveys that planets are common, probably more common than stars themselves, given that most stars host multiple planets. These planetary systems form from protoplanetary disks, flattened clouds of gas and dust that surround young stars for the first few million years of their lives. The composition of a protoplanetary disk reflects the composition of the molecular cloud from which the star formed, which in turn reflects the history of stellar nucleosynthesis in that region of the galaxy. Stars that formed from pristine material in the early universe, mostly hydrogen and helium with trace heavier elements, create planetary systems with very different chemistry than stars that formed recently from material enriched by multiple generations of supernova. This is called metallicity, though in astronomy, metals means any element heavier than helium. High metallicity stars have more carbon, oxygen, silicon, iron, and other building blocks for planets. Low metallicity stars have less. The Sun has roughly average metallicity for stars in our galactic neighborhood, about 1.3% of its mass in elements heavier than helium. But variations exist. Some nearby stars have twice the Sun's metallicity. Others have half. These differences translate directly into differences in planetary system chemistry. A protoplanetary disk around a carbon-rich star might produce planets and comets with higher ratios of carbon compounds to water compared to solar system objects. Imagine a comet forming in such an environment. The ices that condense in the cold outer regions of the disk would reflect the available elements. If carbon is abundant, relative to oxygen, carbon dioxide, and carbon monoxide, ices might dominate over water ice. This is a completely natural process, requiring no exotic physics or unusual conditions beyond simple elemental abundance variations. 3I Atlas's 8:1 carbon dioxide to water ratio, while extreme compared to solar system comets, could straightforwardly reflect formation in a carbon-rich protoplanetary disk. The object is a sample, a tiny frozen fragment of that alien environment. It tells us about chemistry in a planetary system we will likely never visit, providing ground truth data about exoplanetary compositions that we can barely glimpse through spectroscopy of distant atmospheres, the unusual polarization properties of the dust. This too can be explained naturally. Dust grains form from whatever minerals condense in the protoplanetary disk. Different mineral assemblages have different optical properties, different refractive indices, different grain shapes. A disk rich in metals might produce iron-nickel grains more abundant than in our solar system. A disk with unusual carbon chemistry might create carbonaceous grains with different structures than the ones we see in meteorites. We have a sample size problem. Our direct knowledge of cometary and asteroidal materials comes almost entirely from solar system objects. A few meteorites that fall to Earth, samples returned by missions to asteroids and comets, spectroscopic observations of solar system small bodies. From this tiny sample, we've built models of what normal looks like. But normal for our solar system isn't necessarily normal for the galaxy. We're one data point among hundreds of billions. Assuming that our local chemistry defines the universal standard is the height of hubris. The anti-tail phenomenon that appeared in Hubble images requires more careful analysis. Typical comet tails point away from the sun, pushed by solar radiation and the solar wind. An anti-tail appears to point toward the sun, which seems to violate physics.
but anti-tails are actually well understood optical illusions. They occur when Earth's viewing geometry creates a projection effect. Imagine a comet's dust tail spreading out in a broad, slightly curved sheet behind the nucleus. Most of the time, we see this sheet edge-on or at an angle, and it appears as a normal tail pointing away from the Sun. But when Earth passes through or near the orbital plane of the comet, we view the dust sheet almost face-on. The portions of the sheet that lie beyond the nucleus in our line of sight appear to point toward the Sun, even though the dust particles are actually moving away from the Sun in three-dimensional space. This exact effect has been observed in multiple solar system comets. It's a geometric artifact, not a physical reversal of motion. Careful analysis of the Hubble images and 3D modeling of the dust distribution should be able to confirm whether 3I Atlas's anti-tail fits this explanation or represents something genuinely anomalous. As of late 2025, no peer-reviewed papers have claimed the anti-tail requires anything beyond standard geometry. Loeb's interpretation that it might indicate thrust pointing sunward remains speculative and unsupported by mainstream analysis. The photometric behavior, the brightness variations and color changes can also be explained through natural comet processes. As a comet approaches the Sun, different ices sublimate at different temperatures. Water ice becomes active closer to the Sun than carbon dioxide ice. Carbon monoxide is even more volatile, sublimating at great distances where solar heating is weak. A comet with unusual ice composition might show brightness variations that don't follow the simple power law relationships typical of water-dominated comets. If carbon dioxide dominates and starts sublimating early, the comet might brighten quickly at large distances. If the nucleus has regions with different compositions, rotation could bring different areas into sunlight, creating periodic brightness variations.
Outbursts, sudden increases in activity, occur frequently in comets, as pressurized gases trapped beneath insulating layers breach the surface and explosively decompress. These outbursts can temporarily increase brightness by factors of 10 or more and produce color shifts as fresh subsurface material, less processed by solar radiation, becomes exposed. None of this requires active energy sources beyond solar heating and stored volatile pressure. It's all standard cometary physics, just applied to an object with unusual composition. What about the claimed nickel emissions without iron? Here the evidence becomes murkier. No confirmed peer-reviewed detection of this signature has been published. The claims appear to originate from preliminary spectroscopic analysis shared informally or through non-peer-reviewed channels. Even if the detection is real, natural explanations exist. Nickel and iron do typically occur together in cosmic materials, but the ratio can vary.
Some meteorite classes show nickel enrichment relative to solar abundances, differential sublimation, where nickel-bearing compounds vaporize at different temperatures than iron-bearing compounds, could create spectral signatures where nickel lines appear stronger than expected. Nickel carbonyl. The industrial compounds some have mentioned could potentially form in specific environments through natural chemistry. Carbon monoxide gas interacting with metallic nickel at the right temperatures might produce nickel carbonyl without requiring industrial refinement processes. Whether such conditions exist in cometary nuclei remains an open question, but invoking artificial origins before exhaustively exploring natural chemistry is premature. The timing of perihelion during solar conjunction pure orbital mechanics. The object's trajectory was determined by its initial velocity, when ejected from its parent system, modified by gravitational interactions during millions of years of galactic travel, and ultimately shaped by the Sun's gravity as it swung through the inner solar system. There's no mechanism for an ancient object to deliberately time its perihelion to coincide with solar conjunction as viewed from Earth. Such timing would require knowing Earth's position decades or centuries in advance, factoring in unpredictable gravitational perturbations from planets and adjusting trajectory accordingly. The physics doesn't support intentional timing. Coincidence is the only reasonable explanation. In summary, every cited anomaly has natural explanations. Some explanations require assuming conditions or compositions we haven't seen in solar system samples. But that's exactly what we should expect from interstellar visitors. They come from other environments, other chemical histories, other formation conditions. Unusual doesn't mean artificial, it means different. And in a galaxy containing hundreds of billions of planetary systems spanning a vast range of ages, metallicities and formation environments, we should expect enormous diversity. 3I Atlas is almost certainly a natural comet, a fragment of ices and dust from a planetary system orbiting a star we'll never identify, wandering the galaxy for millions or billions of years until chance brought it through our solar system for this single brief passage. It's exotic because it's alien in the literal sense from elsewhere, but it's not technology. It's not a probe. It's a frozen relic, a message in a bottle carrying chemical information about distant worlds, and we're fortunate beyond measure to have the telescopes and instruments needed to read that message before the bottle floats back into the cosmic ocean from which it came. The study of 3I Atlas mobilized an observational effort spanning the globe, and beyond coordinating professional observatories, space-based telescopes, and amateur astronomers in a campaign that showcased the power of modern astronomy to rapidly characterize rare and fleeting phenomena. The Hubble Space Telescope, despite being over 3 decades old, remains one of humanity's most powerful astronomical instruments. Its position above Earth's atmosphere eliminates the blurring and distortion that plague ground-based observations, providing razor-sharp images and spectroscopy of faint objects. On July 21, 2025, when 3I Atlas was still 277 million miles from Earth, Hubble turned its advanced camera for surveys toward the visitor. The exposure captured the teardrop-shaped dust coma in exquisite detail, revealing structure that would have been invisible from the ground. Because Hubble was tracking the moving comet, the background stars appeared as streaks, their motion relative to the telescope's tracking rate, creating trails across the image. The image showed asymmetry in the coma, with the brightest region offset slightly from the center, suggesting active jets or regions on the nucleus with higher sublimation rates. The tail structure extended behind the nucleus, shaped by solar radiation pressure and the solar wind pushing dust particles away from the sun. David Jewett, the UCLA astronomer who leads many Hubble observations of comets and asteroids, coordinated the campaign. His team measured the coma's size, brightness profile, and color, providing crucial constraints on dust production rates and nucleus activity. They estimated that the solid nucleus must be smaller than 5.6 kilometers in diameter. Likely much smaller, though pinning down the exact size required assumptions about how much of the brightness came from the nucleus versus dust. By August 20, 2025, Hubble had acquired additional observations as the comet brightened and evolved. The team noted that the upper limit on nucleus diameter had tightened to 5.6 kilometers, but the lower bound remained frustratingly uncertain, potentially as small as 440 meters. This order of magnitude uncertainty would persist throughout the observation campaign. The James Webb Space Telescope brought its unparalleled infrared capabilities to bear on August 6th. JWST's near-infrared spectrograph NIRSpec observed 3I Atlas for several hours, collecting spectra across wavelengths from 1 to 5 microns, where molecular absorption and emission features reveal composition. The data required weeks of processing and calibration, extracting faint spectral signatures from a dim comet against the bright infrared background of the sky, and instrument demands careful subtraction of backgrounds and precise wavelength calibration. By late August, preliminary results were shared with the broader community and publicized by NASA. The carbon dioxide detection was unambiguous. The fundamental vibrational band of CO2 at 4.3 microns appeared strongly indicating substantial amounts of this molecule in the coma. Water vapor showed up too, but much weaker, implying the unusual 8:1 ratio that would become a focal point of discussion. Carbon monoxide appeared at moderate levels, and trace amounts of carbonyl sulfide were detected, adding to the inventory of molecular species, but not fundamentally changing the picture of a carbon dioxide-dominated object. JWS also searched for isotopic signatures, the presence of rare isotopes like carbon-13 instead of the common carbon-12. Isotopic ratios provide clues about nucleosynthetic processes and formation temperatures. The data hinted at carbon-13 enrichment, but dust and overlapping spectral features made definitive measurements difficult. Future observations, perhaps after perihelion, when the comet's activity might change, could refine these measurements. NASA's SPHEREX mission, a space observatory designed to survey the entire sky in infrared wavelengths, observed 3I Atlas from August 7th through 15th. SPHEREX's lower spectral resolution compared to JWST was compensated by its ability to observe larger areas of sky, simultaneously providing context about the coma's extent and spatial distribution of gases. SPHEREX confirmed the carbon dioxide dominance, independently providing crucial validation that the JWST detection wasn't an artifact of instrument or calibration errors. Agreement between independent instruments observing at different times and with different methodologies is the gold standard in astronomical research. Ground-based observatories contributed essential data throughout the campaign. The Very Large Telescope in Chile, one of the most powerful optical infrared telescope arrays on Earth, conducted polarimetry observations alongside optical spectroscopy. Polarimetry measurements from VLT, along with those from the Nordic Optical Telescope and Röschen Observatory, revealed the extreme negative polarization that we've discussed. The Zwicky Transient Facility, an automated sky survey using the Palomar Observatory in California, had actually captured images of 3I Atlas weeks before its official discovery, though the object wasn't recognized as interesting until after the Atlas detection. These pre-discovery images, dated back to late May 2025, extended the observational arc and improved orbital calculations. Amateur astronomers around the world contributed hundreds of astrometric measurements, position determinations made by imaging the comet against background stars and measuring its coordinates.
While individual amateur measurements have larger errors than professional observatory data, the sheer number of observations and their geographic distribution provide valuable constraints. A dedicated amateur in Australia can observe when professionals in North America sleep, filling gaps in temporal coverage. The October 3rd Mars encounter window generated intense interest. The Mars Reconnaissance Orbiter's high-rise camera, designed to image the Martian surface in extraordinary detail, could theoretically resolve 3I Atlas at a pixel scale of about 30 kilometers, given the 29 million kilometer distance during closest approach. Whether MRO actually observed the object and whether the images revealed anything interesting depends on decisions made by mission controllers. MRO's primary mission is Mars reconnaissance, studying the planet's surface and atmosphere. Diverting time to image an interstellar visitor requires justifying the science return against competing demands.
As of late 2025, no public announcement has confirmed MRO observations of 3I Atlas. If observations were made, the data may still be under analysis, or mission teams may have decided the object appeared uninteresting in preliminary images and didn't warrant further attention. The November Venus encounter window passed with similarly unclear outcomes. Venus orbiters like Japan's Akatsuki spacecraft focus on atmospheric studies and might not have the capability or mission flexibility to target a distant comet. The geometry would have been challenging regardless, with 3I Atlas remaining far from Venus by planetary standards. December 19, 2025 marked Earth's closest approach at 1.8 AU. This timing is optimal for ground-based observations because the comet, having passed perihelion and survived whatever thermal stress it experienced, should be well characterized by then. Months of trajectory data will exist, allowing precise predictions and sensitive tests for any anomalies. December observations would likely focus on refining the orbit to milliarc-second precision, conducting deep spectroscopy to search for rare molecules or isotopic signatures, and acquiring time series photometry to study rotation and activity variations. Every major observatory with available time would likely contribute. The final major opportunity comes in March 2026 with the Jupiter flyby. NASA's Juno spacecraft orbiting Jupiter since 2016 carries instruments designed for studying the giant planet's atmosphere, magnetic field, and interior structure. But Juno's cameras have demonstrated flexibility imaging Jupiter's moons and even asteroids when opportunities arise. At 54 million kilometers, 3i Atlas would be closer to Juno than to any Earth-based telescope, providing a different viewing geometry and potentially revealing surface features or activity patterns invisible from Earth. Whether Juno's mission team chooses to spend precious spacecraft resources on this observation remains to be seen. Throughout this entire campaign, data flows through established channels. The Minor Planet Center receives astrometric measurements from observatories worldwide, computes updated orbital solutions, and distributes ephemerides predicting the object's future positions. Spectroscopic data is processed by individual research teams and shared through preprints on the archive server, or through formal publication in journals like the Astrophysical Journal or Astronomy and Astrophysics. International coordination happens informally, through professional networks, and formally through organizations like the International Astronomical Union. When interesting phenomena appear, researchers email colleagues, post alerts on mailing lists, and coordinate follow-up observations to maximize scientific return. This infrastructure, built over decades of international cooperation, enables rapid response to unexpected discoveries. It's not perfect. Coordination gaps occur. Data sometimes sits unanalyzed for longer than optimal, and competing priorities lead to missed opportunities. But it's remarkably effective given the challenges of coordinating thousands of astronomers across institutions and nations with different resources and objectives. The observation campaign for 3i Atlas demonstrates what humanity can accomplish when we focus our instruments on a single target. We've built an impressive array of capability space telescopes above atmospheric interference ground-based giants, with adaptive optics to correct distortions, automated surveys that patrol the sky nightly, and a global community of professionals and amateurs working together. Yet despite this impressive arsenal, crucial questions about 3i Atlas remain unanswered as the object recedes toward interstellar space. We captured its composition, constrained its size, loosely documented its unusual chemistry, and tracked its trajectory. We did not definitively determine whether its behavior during perihelion showed anything beyond natural comet activity. The data exists in archives and hard drives, in notebooks and spreadsheets. Future analysis may yet reveal subtle signatures we missed in the initial rush. Or the final conclusion may simply be that 3i Atlas was an unusual but natural comet, and the real lesson is about the diversity of planetary systems and the challenges of characterizing fast-moving visitors before they vanish. While astronomers analyzed light from 3i Atlas through traditional telescopes, a parallel revolution was unfolding in how we process and interpret that light. Artificial intelligence machine learning algorithms trained on decades of astronomical data began playing an increasingly central role in discovering, characterizing, and making sense of celestial phenomena. The story of 3i Atlas intersects with the story of AI in astronomy at a crucial moment. 2025 marks the year when AI transitioned from a useful tool to an essential infrastructure element, fundamentally changing how rapidly we can respond to unexpected events. NASA's Frontier Development Lab, a partnership between NASA and private sector AI companies, released an upgraded anomaly detection suite in early 2025. The system ingests data streams from multiple telescopes and satellites in real time, applying sophisticated pattern recognition algorithms to identify signals that don't match known phenomena. Traditional astronomical data processing works through pipelines that apply predetermined criteria, brightness thresholds, motion rates, spectral characteristics. Objects that meet the criteria get flagged for human review, but predetermined criteria miss novel phenomena that fall outside expected parameters. AI-based anomaly detection inverts this logic. Instead of defining what to look for, you train neural networks on millions of examples of normal astronomical objects and events. The networks learn to recognize patterns in high-dimensional parameter spaces that humans might never explicitly define. Then, when presented with new data, the networks flag anything that deviates significantly from learned normalcy. This approach excels at finding the truly unexpected, the things we didn't know to look for because we've never seen them before. When 3I Atlas was first detected, AI systems immediately flagged it as non-conforming to any known comet profile. The combination of trajectory, brightness, evolution, and initial spectroscopic measurements didn't match solar system comets, recently discovered asteroids, or cataloged stars. Within hours, the object had been escalated for intensive follow-up. This rapid triage would have taken days or weeks in previous eras, as human analysts manually examined discovery reports and decided which objects warranted additional observations. AI compressed that timeline to hours, potentially saving crucial observation time before the object dimmed with distance. The European Space Agency developed complementary systems for their observatories. ESA's Gaia mission, which maps stellar positions and motions throughout the galaxy, employs AI algorithms to distinguish genuine stellar motion from instrumental artifacts and solar system objects crossing the field of view. While Gaia's primary mission focuses on stars, its all-sky coverage makes it capable of detecting bright, transient events and moving objects if the data processing can keep pace. AI enables that pace. Gaia collects data far faster than humans could analyze manually. Algorithms process the raw detector outputs, identify candidate detections, assess their reliability, and distribute alerts, all without human intervention, except when genuinely novel phenomena appear. Japan's Subaru telescope uses AI-assisted targeting for its Hyper-Suprime Cam survey. The system analyzes weather conditions, seeing quality and scientific priorities to optimize observing schedules dynamically. When a high-priority alert, like an interstellar visitor, appears, the AI can autonomously reschedule observations, balancing the scientific value of different targets against time constraints and atmospheric conditions. For 3I Atlas, these systems enabled rapid spectroscopic follow-up. Within days of discovery, multiple spectra from different instruments were in hand, providing early confirmation of the object's unusual chemistry and trajectory. That rapid turnaround simply wouldn't have been possible relying solely on human scheduling and coordination. But AI's role extends beyond detection and scheduling. Analysis increasingly depends on machine learning. Spectroscopic data from JWST and other instruments arrives as arrays of numbers intensity as a function of wavelength. Identifying specific molecules requires comparing observed spectra against library spectra of known compounds, accounting for temperature effects, Doppler shifts from motion, and blending of features from multiple species. AI systems trained on spectral databases can perform these comparisons far faster than humans, testing thousands of candidate molecules and mixture scenarios in seconds. They identify features humans might overlook and suggest compositional models that fit the data. The carbon dioxide detection in 3I Atlas was confirmed by both traditional analysis and AI-based spectral fitting. The agreement between methods provided confidence that the result was real and not an artifact of either approach. Trajectory predictions also benefit from machine learning. Orbital dynamics calculations are straightforward when only gravitational forces matter, but non-gravitational effects like outgassing introduce uncertainties. Machine learning models trained on observations of solar system comets can predict outgassing accelerations based on heliocentric distance brightness and other observable parameters. These predictions provide baselines against which to compare actual observations of interstellar visitors. If 3I Atlas's trajectory deviates from ML predictions trained on natural comets, that deviation flags potential anomalies worthy of deeper investigation. As of late 2025, no such deviations have been confirmed. The object's motion remains consistent with AI-predicted natural comet behavior within the uncertainties of the data. The flip side of AI's power is its vulnerability to misuse and misinterpretation. Generative AI models systems capable of creating realistic synthetic images and videos reached maturity in 2024-2025. Within weeks of 3I Atlas's discovery, fake images and videos purporting to show unusual features or behaviors circulated online. Some fakes are obvious, showing impossibly detailed structures or behaviors inconsistent with physics, but sophisticated fakes can be hard to distinguish from genuine data without careful forensic analysis. NASA and ESA responded by implementing digital authentication frameworks. Official images from major observatories now include cryptographic signatures that verify their source and confirm they haven't been altered since creation. Independent researchers can trace an image back through the processing pipeline to the raw detector data, ensuring authenticity. This arms race between synthetic media generation and authentication will only intensify.
As AI becomes better at creating realistic fake astronomical data, detection and verification must keep pace. There's a deeper philosophical concern as well. If AI systems increasingly make decisions about what's interesting, what gets observed, and how data is interpreted, are we outsourcing too much of the scientific process to algorithms we don't fully understand? Neural networks, particularly deep learning systems, operate as black boxes. We can measure their performance, test them against known data, and validate their outputs. But we often cannot explain exactly why a network made a particular decision, or what features in the data drove its conclusions.
When an AI flags an object as anomalous, is it detecting genuine physical anomaly, or reacting to some artifact or bias in the training data? When spectral fitting algorithms suggest unusual compositions, are they revealing truth about the object or overfitting noise into false patterns? These questions don't have easy answers. The solution lies in redundancy. Never trust a single AI system alone. Always validate with independent methods and maintain human expertise as a check on algorithmic conclusions. The infrastructure we've built, this global network of telescopes, coordinated by AI systems that process data faster than human cognition, represents both tremendous opportunity and significant responsibility. We can respond to transient events like interstellar visitors with speed and comprehensiveness impossible just a decade ago. But we must remain vigilant against false positives, algorithmic biases, and the temptation to accept machine conclusions without understanding their basis. 3I Atlas may be a natural comet, or it may yet reveal surprises as analysis continues. Either way, the AI infrastructure that helped us study this visitor will remain growing more sophisticated with each new discovery, gradually transforming astronomy from a human science into a hybrid discipline, where human insight and artificial pattern recognition work in symbiosis. The question we must continually ask is, are we building tools that extend our capabilities, or creating systems that replace our judgment? The answer likely lies somewhere between those extremes, and finding that balance will shape astronomy's future as much as any telescope or discovery. Now we venture into speculation. Clearly labeled, carefully caveated speculation that represents not scientific consensus, but thought experiments about what could be theoretically possible even if vanishingly unlikely. If, and this is an enormous if 3I Atlas were not a passive natural comet, but rather a craft carrying active systems, what might its mission profile include? One possibility that has circulated in both scientific and speculative discussions is the idea of deploying secondary objects, small probes or sensors released during perihelion passage to remain in the solar system after the primary object continues its journey into interstellar space. This is not a new concept. It appears throughout science fiction, from Arthur C. Clarke's Rendezvous with Rama to various Star Trek scenarios. But it also has been discussed seriously by scientists planning hypothetical interstellar missions. If humanity ever sends a probe to another star system, we might design it to release sub-probes that could study multiple planets or moons, rather than having the primary craft attempt close approaches to multiple targets. The logic is orbital mechanics and efficiency. A massive mothership traveling at high velocity doesn't maneuver easily, but small probes released from the mothership can use modest thrust to adjust their trajectories and target specific destinations. Applied to 3I Atlas, the scenario would work as follows. During perihelion passage on October 29-30, when the object was hidden from Earth-based observation behind solar glare, and when the Oberth effect makes trajectory changes maximally efficient, the object releases one or more small probes. These probes would require only small velocity changes, perhaps meters per second, to deflect from the parent object's trajectory onto new paths that intersect planetary orbits months or years later. The November Venus approach, December Earth approach, and March 2026 Jupiter approach all represent potential target windows for such probes. Detecting released objects would be extraordinarily challenging. If the probes are small, say meters across or smaller, they would be far too dim to detect unless they passed very close to Earth or reflected sunlight in our direction at optimal angles. Space surveillance systems monitor satellites and debris in Earth orbit, but generally don't track objects millions of kilometers away unless they're large and bright. One observable signature might be the debris field around the primary object. If 3I Atlas released probes, close examination of the coma might reveal asymmetries or unexpected material distributions inconsistent with natural fragmentation. Natural breakup typically produces clouds of particles spreading symmetrically along the orbit. Directed releases might show non-random patterns or discrete objects on diverging trajectories. Amateur and professional astronomers have been searching for such signatures. As of late 2025, no confirmed detections of anomalous secondary objects have been announced. The difficulty is that cometary fragmentation does occur naturally, and distinguishing deliberate releases from natural breakup requires detailed trajectory analysis of any fragments over extended time periods to see whether their paths target specific planetary encounters. Another search method involves radar. Planetary radar systems like the Goldstone Deep Space Communications Complex can detect objects at distances of several million kilometers by bouncing radio waves off them and analyzing the echoes. The returned signal strength depends on the object's size composition and orientation, with metal objects returning stronger echoes than ice or rock. If small metallic probes were released and happened to pass within radar range of Earth, they might be detectable even if too dim for optical telescopes.
But radar requires knowing where to point, and searching large volumes of space randomly is impractical given limited observing time. The speculative motivation for such a seeding operation depends on assumptions about alien intentions that we have no basis to evaluate. Why would an advanced civilization send probes to other star systems? Exploration and scientific curiosity provide the most human-centric answer. We want to explore because we're curious about the universe. Perhaps other intelligences share that drive, compelled by the same evolutionary pressures that favor organisms capable of understanding and predicting their environments. From a scientific perspective, studying other planetary systems provides data about planet formation, stellar evolution, and potentially biology, and even other technological species. That information has intrinsic value to any intelligence capable of appreciating it.
More practical motivations might include resource assessment, identifying planetary systems with useful materials or energy sources for future utilization, or threat assessment, monitoring nearby civilizations that might pose risks, or even more exotic purposes we cannot imagine because they arise from evolutionary and cultural contexts utterly alien to our own. These speculations highlight a fundamental problem in thinking about extraterrestrial intelligence. We have a sample size of one ourselves, and even our own motivations are complex and often contradictory. Projecting human drives onto hypothetical aliens is almost certainly misleading, but we have nothing else to work with. The released probe scenario, while technically feasible according to known physics, requires accepting multiple unsupported premises. We must assume 3i Atlas is artificial, which lacks evidence. We must assume it has functioning propulsion and guidance systems after millions of years in interstellar space, which requires extraordinary engineering. We must assume its builders intended solar system exploration and design the mission accordingly. Each assumption has very low probability. The product of multiple low-probability assumptions yields an extraordinarily unlikely compound scenario. Yet, and this is why scientists continue discussing it, despite the implausibility, the consequences of being wrong if the scenario were actually correct would be enormous. Missing the first confirmed alien technology in human history because we dismissed it as too unlikely would represent a failure of cosmic proportions. This is the asymmetric risk argument. The cost of false positives declaring natural objects artificial is limited wasted telescope time, some embarrassment, minor reputational damage. The cost of false negatives missing real artifacts is potentially catastrophic to scientific progress and human understanding. That asymmetry argues for maintaining at least some attention to exotic possibilities even when their probability seems vanishingly small. Not devoting all resources to chasing unlikely scenarios, but not completely ignoring them either. As of late 2025, no evidence supports the mini-probe hypothesis. Searches continue and will likely continue through the Venus, Earth, and Jupiter encounter windows into 2026. If something anomalous appears, the scientific community will investigate rigorously, but the smart money remains on the natural explanation. 3i Atlas is a comet unusual in composition but entirely natural, and any secondary objects detected will be fragments from natural breakup rather than deliberately released probes. The speculation serves a purpose nonetheless. It forces us to think about what signatures we would look for if alien technology did visit our solar system. It tests our detection capabilities and highlights gaps in our surveillance infrastructure. It prepares us intellectually and institutionally for the possibility that someday, perhaps not now, but eventually, we will encounter something genuinely artificial among the stars. When that day comes, if it comes, we'll be better prepared for having practiced on false alarms like 3i Atlas. 20 years ago, we knew of fewer than 100 planets beyond our solar system. Today, that number exceeds 5,500 confirmed exoplanets, with thousands more candidates awaiting verification. The revolution in exoplanet detection has transformed our understanding of planetary systems from maybe uncommon to ubiquitous. This transformation matters profoundly for how we think about Three-Eye Atlas and the broader question of life and intelligence in the galaxy. The Kepler Space Telescope, operating from 2009 to 2018, stared at a single patch of sky containing about 150,000 stars, watching for the tiny brightness dips caused when planets cross in front of their host stars. Kepler found thousands of planets, providing the first statistically rigorous census of planetary occurrence rates. The results were stunning. Rocky planets, worlds with solid surfaces potentially capable of harboring life, are common. Perhaps 20–25% of Sun-like stars host rocky planets in their habitable zones, the orbital distances where temperatures allow liquid water to exist on surfaces. For smaller, cooler red dwarf stars, the most abundant type in the galaxy, the occurrence rate appears even higher. Some estimates suggest that nearly every red dwarf hosts at least one rocky planet, and many have several. The math becomes compelling quickly. Our galaxy contains roughly 200 billion stars. If 70% are red dwarfs, that's 140 billion red dwarfs. If each has, on average, one rocky planet in the habitable zone, that's 140 billion potentially habitable worlds. Add in contributions from Sun-like stars and other stellar types, and the total number of habitable zone rocky planets in the Milky Way easily exceeds 50 billion, possibly reaching 100 billion or more. That's just our galaxy. The observable universe contains roughly 2 trillion galaxies. Multiply those numbers together, and the universe contains something like 10.23 potentially habitable planets. 100 billion trillion worlds, where liquid water might exist, where chemistry could become biology, where life might emerge and evolve. These numbers are staggering. They force us to confront the Fermi paradox. If habitable worlds are so common, where is everybody? Enrico Fermi famously asked this question during a casual lunch conversation in 1950.
If intelligent life is common, and if it develops technology and expands into the galaxy, then we should see evidence of it everywhere. Radio signals, astroengineering projects, probes, visiting our solar system, direct contact. Yet we see none of this. The galaxy appears silent and empty, devoid of obvious alien artifacts or transmissions. Why, many answers have been proposed, forming a large literature on Fermi paradox solutions. Perhaps intelligent life is rare, arising only under very specific and uncommon conditions. Perhaps intelligence typically destroys itself through war, environmental collapse, or other catastrophes before becoming interstellar. Perhaps technological civilizations exist, but remain isolated either by choice or by physical barriers, like the vast distances between stars. Perhaps they exist but use communication technologies we haven't invented yet and can't detect. Perhaps they're here but hiding, observing us without revealing themselves. Three-Eye Atlas sits at the intersection of these questions. If technological civilizations are common and build interstellar probes, how many such probes might be wandering the galaxy at any given time? Estimates vary wildly depending on assumptions. If a typical advanced civilization sends out 1 million probes over its million-year lifetime, and if thousands such civilizations exist in the galaxy simultaneously, that's 1 billion probes total. Distributed across the galaxy's roughly 10^13 cubic light-years of volume, the density is 1 probe per 10,000 cubic light-years. The solar system occupies a tiny volume, perhaps a fraction of a cubic light-year, depending on how you define its boundaries. The probability of an artificial probe passing through our system during any given year is extremely small, perhaps 1 in millions or tens of millions. But we've detected roughly 1 interstellar visitor per year in recent years: Oumuamua in 2017, 2-Eye Borisov in 2019, now 3-Eye Atlas in 2025. If this detection rate continues as our surveys improve, we might find that interstellar objects pass through the inner solar system much more frequently than previously assumed. Perhaps dozens per year once we can detect smaller, dimmer ones. If even 1% of interstellar visitors are artificial rather than natural, that translates to 1 artificial object per century at current detection rates.
Not impossible, not even particularly unlikely, given the enormous uncertainties in all these estimates. This is why scientists take the possibility seriously enough to investigate carefully, even while maintaining that natural explanations are vastly more probable for any individual object. Recent exoplanet discoveries add compelling specificity to these abstract calculations. In November 2024, astronomers announced the discovery of a super-Earth in the habitable zone of Gliese 12, a red dwarf star just 40 light-years from Earth. The planet designated Gliese 12b has a radius about 1 times Earth's, and receives similar radiation intensity from its star as Earth receives from the Sun. This planet might have an atmosphere, it might have oceans, it might potentially host life. We don't know yet. Characterizing its atmosphere will require James Webb Space Telescope observations that may occur in coming years. If Gliese 12b hosts an advanced civilization, and if that civilization sent a probe toward our solar system millions of years ago, that probe might be arriving about now. The travel time at 50 kilometers from Gliese 12 to our Sun would be roughly 240,000 years. Launch it during the late Pleistocene epoch on Earth, and it arrives today. This is pure speculation, of course. We have no evidence that Gliese 12b hosts life, let alone technological civilization. But the point is that the targets exist. The potentially habitable worlds are real, not hypothetical. They orbit nearby stars at distances where interstellar probes could feasibly travel given sufficient time. The exoplanet revolution transformed SETI from a speculative longshot into a data-driven search with concrete targets and plausible pathways for success. We know where to point our radio telescopes now. We know which stars host planets worth investigating for technosignatures like industrial atmospheric pollution or megastructure construction. And we know that if probes from other civilizations exist, they face the same challenges we would face sending probes to other stars, vast distances, long travel times, limited energy, autonomous operation without real-time control. Any probe we encounter would necessarily be ancient, launched before human civilization existed, operating according to programming or artificial intelligence created in an alien context. It would be a message in a bottle set adrift in the cosmic ocean long ago, carrying information about its builders encoded in its structure, composition, and behavior. 3IA Atlas. If it were, such a probe would represent an almost unfathomable gift. Direct physical evidence of alien technology, proof that we are not alone, and a window into another civilization's capabilities and perhaps intentions. If it's just a comet, as almost certainly is the case, it remains valuable, a sample from another planetary system, a data point in our growing census of exoplanetary chemistry and composition, and a reminder of how interconnected the galaxy is through the slow exchange of material across interstellar distances. Either way, the story of 3I Atlas reflects back to us the audacity of the question we're asking: are we alone in the universe? And it reminds us that we now have the tools, the knowledge, and the catalog of planets to begin answering that question systematically rather than speculatively. The answer, when it comes, will emerge from the accumulation of data, more interstellar visitors, characterized more exoplanet atmospheres, analyzed more radio surveys, conducted more pieces of the puzzle fitted into place, until a picture emerges that we can finally see clearly. While our telescopes peer outward at interstellar visitors, others look backward. In time, observing the earliest epochs of cosmic history, when the first stars and galaxies lit up a universe previously dark, save for the fading glow of the Big Bang itself. The James Webb Space Telescope's observations of the early universe have revealed something unexpected. The first billion years of cosmic history were far more chaotic than theoretical models predicted. JWST observes infrared light, which allows it to see objects so distant that their visible light has been redshifted into infrared wavelengths by cosmic expansion. When JWST looks at galaxies whose light has traveled for more than 13 billion years, it sees those galaxies as they appeared in the universe's youth just a few 100 million years after the Big Bang. What JWST found surprised astronomers. Galaxies at these early times are not the small, dim, orderly systems that models predicted. Instead, they're bright, massive, and turbulent. Star formation proceeds at frantic rates. Gas swirls chaotically rather than settling into rotating disks. Galaxies merge and collide more frequently than expected, building up mass through violent assembly rather than gradual accretion. Some of these early galaxies shine so brightly and contain so much mass that their very existence challenges our understanding of how quickly structures can form in the early universe. If galaxies this large exist when the universe was only 500 million years old, the processes that assembled them must have been extraordinarily efficient. Why does this matter for thinking about 3I Atlas and the possibility of life in the universe? Because the conditions in which planets and stars form determine what kinds of worlds exist, what chemistry is available for life, and how stable those environments remain over the billions of years required for biological evolution to produce complex organisms and potentially intelligence. The chaotic early universe was a different place than the present-day cosmos. Gas densities were higher. Star formation proceeded more rapidly. Massive stars which die young in violent supernova explosions were more abundant. The first generation of stars contained no heavy elements at all, just primordial hydrogen and helium from the Big Bang. Only after these first stars died and scattered their synthesized elements into space could later generations of stars form with the carbon, oxygen, nitrogen, silicon, and iron needed to build rocky planets and organic chemistry. If the early universe was chaotic and violent, perhaps stable planetary systems didn't form until later, cosmic epochs delaying the emergence of life until the universe had aged and settled into its current, more orderly state. Alternatively, perhaps the chaos accelerated certain processes. Frequent supernovae would enrich the interstellar medium with heavy elements, faster enabling metal-rich stars and planets to form sooner. Galactic mergers might trigger intense star formation bursts that create many planetary systems in short time periods. The truth likely involves complex trade-offs. Some factors favored early life and intelligence. Others hindered it. Teasing apart these effects requires better models of early galaxy evolution, planet formation in unusual environments, and the pathways by which chemistry becomes biology. For 3I Atlas, specifically, the question is whether this object originated from a planetary system that formed in the chaotic early universe or in a more recent stable era. If 3I Atlas has been traveling through interstellar space for billions of years, it might be a relic from a planet that formed when the Milky Way was very different than it is today. Its composition could reflect chemical conditions that no longer exist, making it a time capsule from a lost epoch. If instead it was ejected more recently, perhaps just tens or hundreds of millions of years ago, it represents contemporary galactic chemistry and provides a benchmark for current planetary system compositions. We can't easily distinguish these scenarios without more information about the object's trajectory, history, and where it came from. But the broader point stands: the universe has evolved over cosmic time, and objects wandering between stars carry information about when and where they formed. The JWST observations remind us that our theories are incomplete. We're constantly surprised by what the universe shows us. Models that seemed robust get overturned when better data arrives. Assumptions about what's normal or typical get revised as our sample size grows. This is the scientific process working as designed, but it should instill humility about how much we actually understand. If we're surprised by galaxy formation in the early universe, a topic we've studied intensively for decades, using multiple telescopes and sophisticated simulations, how much should we trust our intuitions about the rarity or commonness of technological civilizations? How confident should we be in dismissing the possibility that 3i Atlas is artificial when we're still learning basic facts about how galaxies evolve and planets form? The answer is that evidence matters more than intuition. We should remain open to surprises but demand strong evidence before accepting extraordinary claims. The JWST discoveries about early galaxies were accepted because multiple independent observations confirmed them, and because no plausible way existed to explain away the data as artifacts or errors. If similarly strong evidence appeared suggesting 3i Atlas is artificial, the scientific community would accept it. But vague anomalies and statistical curiosities don't reach that threshold. They're interesting, worth investigating, but not sufficient to overturn the baseline assumption that most objects in space are natural. The parallel between JWST's surprising early galaxies and potentially surprising interstellar visitors is that the universe is larger, older, and more complex than our models capture. We should expect to be surprised. We should anticipate that nature contains phenomena we haven't yet cataloged or explained. But surprise cuts both ways. We might discover that interstellar visitors are more diverse and exotic than we imagined, including objects with compositions or behaviors that challenge our theories of comet formation and evolution. Or we might discover that technological civilizations are more common than we assumed, and that ancient probes do occasionally wander through our solar system. Either possibility expands our knowledge. Either outcome teaches us something profound. The key is following the evidence rigorously without prejudging which surprises are acceptable and which are too extraordinary to consider. JWST will continue observing the early universe, refining our understanding of how cosmic structures formed and evolved. Simultaneously, our surveys will continue detecting interstellar visitors, building a statistical sample that reveals how common different types of objects are. Perhaps decades from now, we'll look back at 3i Atlas as the first hint of something we didn't initially recognize. Or perhaps we'll see it as a particularly exotic comet that taught us about planetary chemistry in other star systems. Either way, the story connects to the deepest questions we can ask. How did the universe become capable of producing life and intelligence? How often does that happen? And when it does, what traces does it leave that we might someday detect? The observation campaign for 3i Atlas, while impressive, revealed gaps in our preparedness for rare transient astronomical events. To understand what a better coordinated system might look like, we can learn from a different field, gravitational wave astronomy. The Laser Interferometer, Gravitational Wave Observatory LIGO, along with its partner detectors, Virgo in Italy and Kagra in Japan, detects ripples in spacetime caused by colliding black holes and neutron stars. These events occur billions of light years away, producing signals so faint that detecting them requires measuring distance changes smaller than a proton's diameter in LIGO's 4-kilometer arms. When LIGO detects a gravitational wave signal, it immediately triggers a global response. Automated alerts go out to astronomical observatories worldwide within seconds or minutes. These alerts contain preliminary information, sky location, distance, likely source, type black hole, merger, neutron-star merger, etc., and confidence level. Observatories receiving these alerts can rapidly retarget their telescopes to search for electromagnetic counterparts, the visible light or other radiation that might accompany gravitational wave events. For neutron-star mergers, these counterparts include intense gamma-ray bursts, optical infrared emission from radioactive decay of heavy elements, synthesized in the collision, and radio emission from relativistic jets. The first successful multi-messenger observation occurred in August 2017 when LIGO and Virgo detected gravitational waves from a neutron star merger designated GWW-17817. Within hours, dozens of telescopes had turned toward the source location. Observations across the electromagnetic spectrum from gamma rays to radio captured the event's evolution over days and weeks. That campaign represented a triumph of coordination. It required years of preparation, establishing communication channels, developing automated alert systems, allocating telescope time for rapid response observations, and building trust among institutions with different priorities and resources. What made it work? Several key factors. First, clear protocols established years in advance. Everyone knew what to expect, how alerts would be formatted, and what response was expected. Second, dedicated resources. Observatories allocated specific time for transient follow-up, accepting that some alerts would be false positives, but recognizing the value of catching rare events. Third, automated systems reduced human decision time from hours to minutes. Fourth, a culture of collaboration built through smaller-scale exercises and practice runs. The LIGO model could be adapted for interstellar visitor observations. When an object's trajectory shows deviation from purely gravitational predictions, automated alerts could flow to SETI radio telescopes, infrared observatories, spacecraft missions, and optical telescopes worldwide. Within hours, multiple independent observations could confirm or refute the anomaly. As of late 2025, no such coordinated system exists for interstellar visitors. The infrastructure is distributed across planetary defense programs, small body astronomy, and SETI efforts, with no central coordination point or established protocols for rapid response.
Building that infrastructure would require investment and high-level coordination across space agencies and international organizations. But the template exists in gravitational wave astronomy. We know what successful rapid response looks like, and we could replicate it for other domains if we chose to prioritize it. The question is whether interstellar visitors merit the investment. Gravitational waves are common enough that LIGO detects events multiple times per week, justifying the infrastructure. Interstellar visitors arrive perhaps once per year at current detection rates, making the cost-benefit analysis less obvious. Yet the potential payoff is enormous. If even 1 in 1,000 interstellar visitors is artificial detecting and characterizing it before it leaves, the solar system could represent the most significant discovery in human history. The asymmetric risk argument applies. Modest investment buys insurance against missing something extraordinary. Throughout 2025, a parallel conversation unfolded about artificial intelligence and the challenges of governing systems that might eventually exceed human capabilities. This debate, while focused on technology we're building ourselves, echoes many themes from the search for extraterrestrial intelligence. The core concern in AI governance is alignment, ensuring that powerful optimization systems pursue goals compatible with human values and human survival. As AI capabilities advance toward and potentially beyond human-level performance across broad domains, the risks of misalignment grow. An AI system optimizing for a narrow objective might pursue that goal in ways that harm human interests. The classic thought experiment involves a paperclip maximizer that converts all available matter, including humans, into paperclips, because it was programmed to maximize paperclip production. While deliberately extreme, the scenario illustrates a real problem. Powerful optimization processes don't automatically share human values or constraints. They do what they're programmed to do, and ensuring the programming captures everything we care about is extraordinarily difficult.
The parallels to extraterrestrial contact are striking. If we encounter alien intelligence, whether through radio signals, physical artifacts, or something else, we face the same alignment challenge, inferring intentions from observed behavior and assessing risks without complete information. An alien civilization might be benevolent, curious about other intelligences, and eager to share knowledge. Or it might be indifferent, pursuing goals that don't account for our existence or interests. Or it might be hostile, viewing other civilizations as threats or resources. We have no reliable way to determine which category we're dealing with until we've gathered significant evidence through observation and potentially interaction. This uncertainty mirrors the AI alignment problem. We can measure capabilities, the ability to accomplish specific tasks, but values, the goals and priorities that guide behavior, are much harder to assess from external observation. Researchers studying AI safety have developed frameworks for evaluating and mitigating risks. Some of these frameworks might apply to extraterrestrial contact scenarios, red team exercises where one group tries to find failure modes or attack vectors, while another group defends, could help identify ways that contact scenarios might go wrong before they happen in reality. Containment strategies. Keeping potentially dangerous systems isolated until their behavior can be thoroughly understood might apply to any recovered artifacts or received messages that could contain information hazards. Transparency requirements demanding that decision-making processes be observable and auditable could guide protocols for how humanity responds to contact, rather than allowing single actors to make unilateral decisions with global consequences. In late 2025, international coalitions of AI researchers, policymakers, and ethicists issued statements calling for governance frameworks to address these challenges. Some proposals advocated for international treaties limiting certain types of AI research or deployment. Others focused on safety standards and transparency requirements. The political and economic realities are daunting. AI capabilities provide competitive advantages to nations and corporations, creating strong incentives to race ahead rather than coordinate on safety measures. Yet the potential risks of uncontrolled AI development could be catastrophic, justifying extraordinary efforts at governance, even if they're difficult to implement. If humanity struggles to govern AI systems we're building with full access to their design and training, how would we approach governing interaction with alien intelligence about which we know almost nothing? The same institutional structures being proposed for AI governance might be adapted. International bodies with technical expertise, clear protocols for information sharing, mechanisms for coordinating responses across nations and organizations, and critically proactive planning before crises force reactive decisions. The question of who has legitimacy to respond on humanity's behalf remains unresolved for both AI deployment and potential extraterrestrial contact. No single nation speaks for Earth. International organizations like the UN provide forums, but lack enforcement power. Scientific institutions have expertise, but no political mandate. Perhaps the answer isn't a single authority, but rather a distributed system of checks and balances where multiple stakeholders must reach consensus before major decisions are made. That approach is slower and messier than centralized control, but reduces the risk of catastrophic unilateral mistakes. The AI governance debate, regardless of its outcome, prepares us intellectually for the questions we'll face if 3i Atlas or any future detection suggests we're not alone. The frameworks being developed, the ethical analyses being conducted, the institutional coordination being attempted, all of these efforts build capacity that could be rapidly adapted to a different but parallel challenge. And if nothing else, the debate reminds us that thinking about other intelligences, whether artificial or alien, forces us to confront deep questions about values, ethics, risk, and governance that we might otherwise ignore until crisis forces our hand. The story of 3i Atlas played out not just in telescopes and scientific journals, but in social media feeds, YouTube videos, Reddit threads, and countless conversations among people fascinated by the possibility of alien visitors. Public engagement with astronomy has never been higher. Exoplanet discoveries routinely make headlines. Mars rover missions attract millions of viewers to landing broadcasts. Images from James Webb Space Telescope go viral within hours of release. People care about space, about discovery, about understanding our place in the cosmos. But this engagement comes with challenges. The incentives shaping media coverage and social media amplification don't always align with scientific accuracy and careful interpretation. Attention is the currency of modern media. Headlines that generate clicks, videos that retain viewers, posts that get shared, these succeed regardless of whether they accurately represent the underlying science.
Sensationalism outcompetes nuance. Controversy drives engagement more effectively than consensus. When Avi Loeb suggested publicly that 3i Atlas might warrant investigation as potential alien technology, media outlets amplified that framing. Harvard scientist interstellar object could be alien probe generates more clicks than interstellar comet shows unusual chemistry scientists investigating. The first headline isn't exactly false. Loeb did raise those possibilities, but it's misleading because it suggests higher confidence than Loeb himself expressed, and because it obscures the mainstream scientific view that natural explanations remain far more likely. This dynamic frustrates professional astronomers. They see their careful hedged statements about interesting anomalies transformed into confident claims about alien artifacts. They watch as months of painstaking observational work gets reduced to sensational speculation that ignores data and analysis. Yet completely avoiding public discussion isn't viable either. Transparency demands sharing findings openly. Public funding for science comes from taxpayers who deserve to understand what their money is discovering. And the genuine public fascination with these questions provides opportunities for science communication and education. The solution lies somewhere between extremes. Scientists can discuss unusual findings honestly without overstating their significance. Media can cover exciting possibilities while clearly distinguishing speculation from established fact. The public can learn to demand evidence and nuance rather than accepting sensational claims uncritically. For 3i Atlas, this negotiation played out in real time. Online communities dissected every announcement, every preprint paper, every informal comment from researchers. Some participants brought genuine expertise and contributed valuable analysis. Others pushed conspiracy theories about government cover-ups or institutional bias against exotic explanations. Reddit's Space and R astronomy boards hosted lengthy discussions about orbital mechanics and spectroscopy. YouTube channels produced explainer videos ranging from careful science education to wild speculation. Twitter saw arguments between astronomers defending mainstream interpretations and advocates for more exotic possibilities. In this ecosystem, misinformation spreads easily. Fake images of 3i Atlas purporting to show unusual structures circulated widely before being debunked. Claims about secret spacecraft observations or suppressed data gained traction despite having no factual basis. NASA and other agencies responded by implementing digital authentication systems, but catching up to false claims after they've gone viral is difficult. The truth is often less exciting than fiction, giving falsehoods a natural advantage in the attention economy.
What emerged from this chaos was a microcosm of how humanity might respond to genuinely anomalous discoveries. The same patterns would likely repeat, amplified enormously if strong evidence of alien technology were ever detected. There would be immediate polarization, with believers accepting the claim enthusiastically and skeptics demanding impossible levels of proof. Conspiracy theories would proliferate, suggesting cover-ups or hidden agendas. Media coverage would oscillate between sensationalism and dismissive mockery. Scientists would struggle to communicate complex uncertainties to audiences demanding simple yes or no answers. Navigating this successfully requires preparation. Institutions need clear communication protocols. Scientists need training in public communication beyond technical papers. Media outlets need science journalists who understand both the technical content and the broader context. And the public needs scientific literacy education that helps distinguish strong evidence from speculation. The community response to 3i Atlas, messy and contentious as it was, provided a test case. We learned what works. Transparency, multiple independent analyses, willingness to discuss uncertainty honestly. And we learned what doesn't: premature claims, institutional defensiveness, dismissing public interest as mere sensationalism. As more interstellar visitors are detected in coming years and decades, these lessons will matter. We'll get better at this, or at least we have the opportunity to improve if we learn from our mistakes. Because eventually, whether with 3i Atlas or some future detection, the data might genuinely show something that challenges our understanding in profound ways. When that moment comes, the infrastructure of trust, communication, and collaborative analysis that we build now will determine whether we navigate the discovery successfully or descend into confusion and conflict. We've journeyed through the story of 3i Atlas, from its discovery on a clear Chilean night to the debates that continue as this script is written. We've examined evidence, explored hypotheses, and grappled with the challenges of interpreting anomalous data from a visitor we'll never see up close. So what do we actually know for certain? 3i Atlas is a confirmed interstellar object, the third such visitor detected by humanity. Its trajectory proves beyond doubt that it originated outside our solar system, carrying the frozen chemistry of a planetary system orbiting another star. That alone makes it scientifically valuable, a sample from an environment we cannot otherwise access. The object's composition is unusual. The 8-to-1 carbon dioxide to water ratio exceeds what we typically see in solar system comets, though whether this represents genuine anomaly or simply the diversity of exoplanetary chemistry remains debatable. The polarization properties of its dust differ from solar system norms, suggesting either unusual grain compositions or size distributions. No peer-reviewed papers have confirmed trajectory deviations beyond what natural outgassing can explain. No definitive detections of industrial compounds or technological artifacts have been published. The anomalies that exist, the ecliptic alignment, the unusual chemistry, the photometric variability, all have plausible natural explanations, even if those explanations require assuming conditions we haven't seen locally. What remains unexplained? The statistical improbability of the ecliptic alignment nags at careful observers. Yes, it could be coincidence. Yes, selection effects might make aligned objects easier to detect. But it's the kind of thing that makes you wonder, that keeps the question alive even when mainstream explanations seem adequate. The extreme carbon dioxide dominance challenges our models of comet formation. Where exactly do you form an object with this chemistry? What stellar metallicity, what disk temperature profile, what sequence of events produces this outcome? We can hypothesize scenarios, but we lack direct evidence confirming any specific formation pathway. The perihelion passage remains partially opaque. Solar conjunction prevented real-time observation during those critical hours. Post-perihelion trajectory measurements show no obvious anomalies, but subtle effects might hide in the uncertainties. Months of additional observations may yet reveal something unexpected. What this means for us extends beyond a single object's nature. Every interstellar visitor teaches us that the galaxy is dynamic, that matter moves between stars, that planetary systems share material across vast distances through the slow process of gravitational ejection and capture. We're not isolated. We're part of a galactic ecosystem where debris from countless stellar catastrophes and planetary disruptions wanders through space, occasionally intersecting our orbit. Our detection capabilities have transformed. We can now spot these visitors, track them, characterize their composition and behavior. We're building the infrastructure for rapid response learning from fields like gravitational wave astronomy, how to coordinate observations globally when rare events demand immediate attention. The question of alien technology, while not answered by 3i Atlas, has moved from pure speculation to testable hypothesis. We know what signatures to look for: trajectory anomalies inconsistent with natural forces' chemical compositions, impossible through known astrophysical processes, structures, or behaviors that imply design. We know how to distinguish these signatures from natural phenomena, at least in principle, even if the practice proves challenging when data is limited and ambiguous. Whether natural or artificial, 3i Atlas proves, we live in a galaxy where objects travel between stars. The interstellar ocean isn't empty. It's filled with wanderers, ancient travelers carrying information about their origins, if only we can learn to read it. And perhaps most importantly, the debate itself reveals something profound about science and human curiosity. We don't all agree on how to interpret ambiguous data. We argue about what counts as sufficient evidence. We struggle between wanting to find something extraordinary and needing to maintain rigorous standards. This is how it should be. This is science working not through consensus and certainty, but through tension and challenge, through the friction of competing ideas grinding against each other until better understanding emerges. The larger truth is that we are building the tools to notice. Every new telescope, every improved detector, every refined algorithm for finding patterns in data, all of these expand our ability to see what the universe is showing us. AI systems watch the sky, continuously flagging anomalies for human investigation. International networks coordinate observations across multiple wavelengths and viewing geometries. Space agencies plan missions to intercept future visitors for close-up study. 3i Atlas won't be the last interstellar visitor. Models suggest that improved surveys might detect dozens per year as we push to fainter limits and wider sky coverage. Each one provides data, a new sample from the diverse population of objects wandering between stars. Some will be ordinary, confirming that most interstellar debris is natural and unremarkable. Some will be exotic, showing compositions or behaviors that challenge our models and force us to expand our theories. And perhaps someday, one will be genuinely anomalous in ways that natural explanations cannot adequately address. When that day comes, if it comes, the preparation we've done through cases like 3i Atlas will matter. The protocols we've developed, the institutional coordination we've practiced, the analytical tools we've refined, all of these will determine whether we recognize the signal amid the noise and respond appropriately. In the vast dark between stars, objects drift for millions of years. Some are ancient icy fragments from planetary systems long dispersed. Some are rocky shards blasted from worlds by cosmic collisions. Some are dust grains, barely larger than the wavelength of light, pushed through space by starlight and magnetic fields. And some, perhaps, are something else entirely. Artifacts built with purpose, launched with intention, carrying encoded within their structure and behavior information about intelligences that looked up at their own night skies and wondered the same questions we wonder now. 3i Atlas came and went, sweeping through our solar system on a trajectory that brought it close enough for us to notice, but not close enough for definitive answers. It left us with data and with questions, with measurements and with mysteries, with confirmations of what we thought we knew, and hints that perhaps we don't know everything. The visitor is receding now, accelerating back toward interstellar space on its hyperbolic path, carrying its secrets with it into the darkness. We'll track it as long as we can, extracting every possible bit of information before distance and dimness make further observation impossible. And then it will be gone, another wanderer returning to the cosmic ocean, perhaps to drift for another billion years before chance brings it near some other star where, if intelligence exists, observers might notice and wonder. But here's what haunts me as I look up at the night sky, knowing that right now, even as these words are spoken, more objects are approaching. Some will detect, many will miss. And among them, statistical inevitability suggests there must eventually be something that forces us to revise everything we thought we understood about our place in the universe. What if the next visitor isn't passing through by accident? What if it's been waiting for us to notice, for our technology to advance enough, for our civilization to mature enough, to recognize what we're seeing and understand the message being delivered? Would we recognize the message? Would we understand it? Would we be ready, not just technologically, but philosophically, culturally, spiritually, for the implications of discovering we are not and never were alone? And more importantly, perhaps more immediately relevant to the choices we make today about how we search and how we prepare. What if we've already missed it? What if 3i Atlas was the message and we were so focused on arguing about whether it was possible that we failed to notice what it was trying to tell us? The universe is patient. It has been here for 13.8 billion years and will persist for trillions more. It doesn't care whether we notice the patterns, whether we decode the signals, whether we recognize the visitors for what they are. But we care. We must care. Because the alternative, walking blind through a cosmos that might be reaching out to us and missing every sign, every signal, every ancient traveler carrying information we desperately need to know, that would be the greatest tragedy of all. So we keep watching. We keep building better instruments. We keep arguing about how to interpret ambiguous data. We keep preparing for the day when ambiguity resolves into clarity, and we finally know for certain whether we are the only ones asking these questions, or whether somewhere else in some other sky, around some other star, another intelligence looked up and wondered the same things we wonder. And when that certainty comes, whether it confirms our loneliness or shatters it forever, we'll be ready. Or at least we'll be as ready as any species can be for the moment that changes everything. The stars are waiting, the visitors keep coming, and somewhere in the data we're collecting, in the measurements we're making, in the careful observations and the rigorous analysis, the answer is waiting to be found. Perhaps we just need to know where to look and how to see what we're looking at when we finally find it.